Good evening, Sandeep sir. Sandeep sir, I am audible to you. No, sir, you are not audible.
Hello.
Yeah, it's now audible, sir.
Audio, right?
Welcome, sir.
Yeah. Thank you, madam.
Vani ma'am, can we start now? Sandeep sir, can we start?
Sir, shall we start, sir? Sandeep sir? Sandeep sir?
Yes, madam. Please.
Shall we start, sir?
Yeah, definitely.
Sir, can you please share your screen also, sir, so that our participants can able to see?
Should I need to share my screen?
Yes.
Yes, sir.
I hope you can see it. Right?
Yes, yes.
Yes, sir. Yes, Sandeep sir. So, Dr. Sandeep Singh is a senior lecturer at Cardiff Metropolitan University, UK. He also serves as cluster leader for computer vision, image processing, and represents the British Computer Society. Prior to his current role, Dr. Sandeep was a postdoctoral research fellow in machine learning section of the computer science department at University of Copenhagen, Denmark. In 2022, he was a visiting researcher at University College, Dublin. Dr. Sandeep earned his PhD in computer science vision from the Indian Institute of Technology, IISM, Dhanbad, and his MTech from Motilal Nehru National Institute of Technology, Allahabad, India. He is a fellow of UK Higher Education Academy and a senior member of IEEE. His research focuses on machine learning, deep learning, computer vision, and image video processing. Dr. Sandeep has an extensive publication record in leading international journals and conferences. He has published in top tier venues such as IJCAI, BMVC, EMBC, CVIP, MIE, and EFML. He is a member of editorial board for Signal Image and Video Processing, an international journal of image systems and technology. He also serves on the board of studies at Universal AI University in Mumbai, India, as an external examiner at the London School of Innovation, and reviews research grant proposals for EPSRC, UK, NMRC, Singapore, and Cardiff Metropolitan University. Additionally, Dr. Sandeep is a PhD examiner for several prestigious institutions, including the University of South Wales, Cardiff University, the Indian Institute of Technologies, and National Institute of Technology, India. He has played key role in international conferences, such as serving as an organizing chair and distinguished guest. He has delivered more than 135 expert talks worldwide at prestigious institutions, including Trinity College, Dublin, University College, Dublin, Technical University of Denmark, Cardiff University, multiple Indian Institute of Technology, including IIT Kharagpur, IIT Roorkee, IIT Gauhati, and several others. Now I invite Dr. Sandeep Singh Sengar to deliver the third day session 5 talk for 6 days ATAL online FDP on the topic Deep Learning in Medical Imaging, Advances in knee MRI Segmentation. Welcome you, sir.
Yeah, thank you, madam, for this introduction.
Thank you,
So,
sir.
yeah, good evening, everyone. So here, I'm going to discuss about deep learning in medical imaging today. And so in this talk, first of all, I will start with the introduction of machine learning and deep learning. Then we'll discuss how we can incorporate these machine deep learning techniques in a medical image environment. So before starting this talk, I would like to give you idea about the medical imaging. So I have one more presentation. So here I will discuss about the medical imaging things. Right, most of you might be aware about these techniques. There are different types of medical imaging techniques are there. Let's say X-rays, CT scan, and MRI. So let's start with the basic introduction of these images, so you can have an idea about X-rays. So if you are talking about X-rays, then X-rays are a form of electromagnetic radiations similar to visible light. They are these are in the form of electromagnetic radiations. So whenever we talk about the X-ray, then they produce a high energy, and these X-rays can pass through any of the object, including the body also. So if you're talking for X-rays, like how X-rays will be formed, then when we talk about the X-ray, then in X-ray we have one source and one destination. So sink, we can say sink or destination. There are two different types of machines. So when we'll go for X-ray, then the person, that the radiologist, will ask us to sit like a stand in between of these two machines, right? Source and observer, or like a destination or sink, whatever you call. Then from that source, X-rays will be emerged, and these X-rays will pass through our body. Once these X-rays will pass through our body, then the shadow of these X-rays will be formed on the backside of body, like there is a sink or observer. Then this shadow will be formed on the backside, and this shadow will be just like X-ray film, what we see in hard copy way and all those things. Now, when the X-rays will pass through the body, then like in our body we have bones and muscles, soft tissues, and all those things. So bones contains calcium. So this calcium absorb more energy or more X-rays as compared to the other part. So like when you see the X-ray in a hard copy way, then you find that like the bony part is clearly like separate than the other soft tissue part, because from soft tissue part X-ray passes at a very fast speed, so they are not able to form that carefully. But when they pass through the bony part, then you will see the clear contrast between the other organs and the bony part. So specifically like X-ray we designed for the like bone segmentation, for bone like classification purpose, or to detect the particular bone. So before going through, like let me show you that a demo, and in this demo, like a small demo, you will find it interesting. can't hear a voice, then please let me know. Otherwise, we can play it. Okay, so this was the quick introduction, quick overview of X-rays, like how X-rays are formed. I already explained, and the same thing is written here, right? So, like how they like the X-ray observe and all those things, like bony part observe X-ray more than the other part. And why we use X-ray? When are medical X-ray used? So, like to detect bone fracture, certain tumors, and other abnormal masses, pneumonia, or some types of injury, calcification, foreign object. So for all these purpose, like we use X-rays. Now the next type of image, next type of medical image is computed tomographic CT image. So we can say the CT and X-ray are not much different. The X-ray image is a two-dimensional, and a CT we can say is the three-dimensional version of that two-dimensional. So to understand it in a better way, like this is like a computed tomography machine in front of you. In this machine, we have patient table where like we lay the patient, and then we have a gantry, and inside that gantry, like we have gantry aperture. So in this gantry aperture, like we have X-ray device. So once like patient go inside that machine, then this gantry aperture rotate from like one place, like in a rotate in a like 360 direction way, in a circular way. So once this gantry aperture rotate, then during rotation time, it capture the X-rays. Just like X-rays we discussed earlier, it capture the two-dimensional slices. Now, like when like we realize, the radiologist realized the sufficient number of two-dimensional slices have been collected, then we stop that procedure. Then later on, these two-dimensional slices form a three-dimension structure, three-dimension like image. So that three-dimension image or three-dimension scan is called CT image. So why we use CT scan? Because we can see the detailed information in CT image as compared to the X-ray. So here also, like we have one more demo related to that. And a demo, whatever is available in the demo, it is written here, right? In a like text part. So let's see. Okay, so about uh, the city one. And now we can use the CT scan for various purpose, like for like different like identifying disease or injury with various regions of body. Right? And CT scan can be held, can be used for heart, may be ordered when various types of heart disease or abnormality is suspected. Right? A stroke, hemorrhage, or so like a blood clot, and or like for many other purpose, we can use this CT scan. Now, next different type of image is magnetic resonance imaging (MRI). It is completely different than X-rays and CT scan image. This is also the three-dimension image, but three-dimension, but based on non-invasive imaging technology. Non-invasive imaging technology means here we don't pass any rays like from the like body. In place of rays, we generate the magnetic field. We generate the magnetic field surrounding the body, surrounding the body. And just like we know about a magnet, right? What magnet do? If we keep magnet near to iron, then they will attract, right? They will attract to each other. In a similar way, here also like we release the magnetic field, and in our body there is a water, and inside water there are proton. So when like we like produce the magnetic field, these protons are aligned towards that magnetic field. These protons are aligned towards the magnetic field. Now after that, once they like completely align, at that time we produce the radio frequency current, right? Radio frequency energy we produce. Using that radio frequency energy, like these protons are try to come back, means they are try to like be aligned with that particular magnetic field, either in a 90-degree or in 180-degree. So during that process, how much energy is released during that process? Like earlier, like this magnet like our protons were aligned with that magnetic field, and later on how much energy is released in like separating both of the magnetic field and the proton. So using that energy we can identify the particular types of organs. So as per the radiologist, different organs release different amount of energy, right? So accordingly, like we can decide like what organs it is, and if it is if any problem is there in any particular kinds of organ, then it will produce a different kinds of energy and different kinds of image. So radiologist can identify using that like what is the problem with that. So let's see the demo of MRI also little bit. So here just you will understand it better way.
Sandeep sir,
Yes, sir.
we are not able to hear your video.
You are not able to hear.
Yes, sir.
It's the third video. Okay. So
No, I just checked with the previous videos. I thought it is just you're saying segmentations alone. So now
oh,
I think there is some audio with all the videos.
let me share it again.
It disrupts the
Now
process.
it's okay.
Yeah, now it's okay, sir.
Okay, so let's start from there.
MRIs use protons, which are abundant in the human body. All protons spin, creating a small magnetic charge. When a strong magnetic field is introduced, as is the case in an MRI machine, the protons align with that field. The MRI technician then introduces a radio frequency pulse that disrupts the proton and forces it either into a 90-degree or 180-degree realignment with the static magnetic field. Since the radio frequency pulse pushed the proton against its nature, once this pulse is turned off, the protons realign with that magnetic field, releasing electromagnetic energy along the way. The MRI is able to detect this energy and is able to differentiate various tissues based on how quickly they release energy after the pulse is turned off.
Accordingly, like we can identify based on this energy, we can identify the particular types of organs, body organs.
Sir, can you, Sandeep sir,
Yes, madam.
can you please replay the first two videos?
First two videos. Okay.
Yeah.
Light is a form of electromagnetic radiation. At some wavelengths, it appears as visible light. At others, it takes the form of radiation we cannot see, such as ultraviolet, infrared, and X-rays. X-rays have very short wavelengths that, unlike visible light, are able to pass right through most tissues in the human body. Since bones contain calcium, a denser material than most other tissues, they are able to stop some of the X-rays and can thus form a shadow. If you place your hand in front of a flashlight, it will cast a shadow on the wall behind it. In a similar manner, X-rays directed at the body produce shadows on the opposite side that can be registered on film or on a digital sensor, so that bones are clearly visible while soft tissues, such as muscle, are shadowy. As a result, the two-dimensional images formed by the X-rays are quite useful in revealing structures within the body and can easily display fractures in bones. A CT scan is an X-ray procedure that creates cross-sectional images with the help of computer processing. CT images are more detailed than conventional X-ray images and can reveal bones as well as soft tissue and organs. A conventional X-ray uses a fixed tube that sends X-rays in only one direction, while a CT scanner uses a motorized X-ray source that shoots narrow beams of X-rays as it rotates around the patient. There are special digital X-ray detectors located directly opposite the X-ray source. As the X-ray passes through the patient, they are picked up by the detectors and transmitted to a computer. Image slices can either be displayed individually in two-dimensional form or stacked together to generate a three-dimensional image that can reveal abnormal structures or help the physician plan and monitor treatments.
Right. So we've got three videos related to X-ray and CT scan and MRI. Hope you understood like how they work. So if you are talking for MRI, then we use MRI specifically for soft tissues. X-rays and CT scan are mainly for like bony part, but like we use MRI for non-bony part like soft tissues, ligament, and like specifically for knee MRI segmentation purpose, brain tumor segmentation purpose, we use this MRI scans. So here we are talking for scan, that means it's a three-dimensional image, and we are talking for slices, then it's a two-dimensional version of that three-dimensional image, right? So this is the overview of just overview of medical imaging. Now I'm going to present the actual content. So let me. So now what I will do, I will start with a deep learning introduction, then how we can apply this medical imaging in deep learning environment. Then we'll discuss different applications, case studies related to NMRI segmentation or some other also if we get time. So let's start this part with one beautiful picture. So there is one picture in front of you, and in this picture like you can see many of the things, and there is a picture as well as along with this image or picture we have one quote: one picture is worth more than thousands of words. So this is one of the famous quote. That means, like, for example, I will give you like 1,000 of words to read, and I will tell you to give answer from that particular text, and in parallel I will give you the image and give answer from that image, right? So then in that case you will prefer image over that particular text. So that means, like, images or all these visualization things have a very important role in our life, and they makes our life very easy. So now that's the reason like this image processing and all those things are quite popular. So now in front of you there is one image data set, we can say, and in this image you can see many of the things. Many of the things means, like, there is one small village, two tractors are there, hill areas are there, different colors of skies are there, right? So many of the things we can see from this image, or many of the things we can interpret from this image data set. We can see all these things. Who we are the human being. We are the human being who can interpret the contents from this image data set. If the same task is done by computer, that means if computer is going to identify, computer is going to tell, then there are hill areas, there are two tractors, a small village, and beautiful colors of sky, then it's called computer vision, right? Computer vision means the computer interprets the contents from image or video data set. So now whatever we are going to talk about in this lecture means deep learning in medical image environment, all are based on, like, computer vision. Whatever, like, information we are going to extract from image data set, that's the computer vision, right? So we will discuss about all these things in detail, and for solving this computer vision problem nowadays mostly we apply the deep learning algorithm. So there's one of the famous diagram in front of you, you might have seen this one. So on the top of this diagram there is artificial intelligence. Artificial intelligence means machine mimic the behavior of a human being. Machine work like a human being. So example of artificial intelligence might be autonomous car and a robot and all those things. The sub part of artificial intelligence is machine learning. Machine learning means learning from experience, learning from data sets. So based on this experience, based on data set, the model can predict the output for unknown input. So one of the very good example, like housing price prediction, or like any disease prediction from medical domain. Then the sub part of machine learning is deep learning. Here, deep learning means it's a bit more advanced than machine learning, where we have a high number of layers, as well as we have high number of parameters, but we expect better accuracy using that deep learning. So if you want to apply deep learning, then the one condition is that you should have a large data set, then only, like, there's a chance of high performance, very good performance. And this deep learning is inspired from, you can say, like, artificial neural network is inspired from human brain neuron, but the deep learning is an extended version of artificial neural network. So indirectly we can say deep learning is also inspired from human brain neuron. And like in human brain there are neurons, and these neurons are connected to each other, and using that connection we take decision, right? So this is about deep learning. And if we talk about the difference between deep learning and machine learning, in machine learning means, like, we have input image, and from this input image we extract the features. We extract the features means human being extract the features. If you're talking for medical imaging, then the radiologist will extract the features. And if you're talking about any other environment, then it might possibly like data scientist or some other data analyst, they will extract the features. Once the manually, like, we will extract the features, then these features will be given as input to the classification model, and we can classify whether it's a car or not a car. So this is the basic mechanism behind machine learning. Then next is a deep learning. In deep learning, we no need to extract the features manually. Means directly we can give a raw input, a raw image as an input, and we can find the output. So feature extraction and classification, all these tasks are done or taken care by this deep learning model. So we can say deep learning is the end-to-end approach. Means just we give input as an image, we generate the output directly. So if we talk about the architecture, different architectures of deep learning, then we have convolutional neural network. Convolutional neural network mainly we use for image recognition, video analysis, and mainly related to image or video processing related things, either medical imaging or non-medical one. Next is recurrent neural network. We use RNN for NLP task purpose like speech recognition, handwriting recognition, machine translation. Then we have a long short-term memory, gated recurrent unit. Same like it's an advance of RNN, and we use for NLP task purpose for handwriting recognition and speech recognition. Then we have deep leap network, deep stacking network. So there are different types of networks are there. On the basis of different requirement, we use these architectures. So if we talk about the convolutional neural network, then there are different approaches of like deep learning, right? Out of that, one is CNN, and CNN mainly we use for image or video data set. So here in this talk, we are talking for the we will discuss for the medical imaging. So medical imaging is we are going to discuss for the image data set. So that's the reason like we should focus on CNN part, right? So let's understand CNN, how CNN work, and how we connect that input to filters, and like we generate the features and all those things that we see. So if you're talking for the CNN, convolutional neural network, where like we have input and we assign importance, means weights on the input, and then in the end we need to learn these weights and biases with the help of these filters. So we'll see this thing later on. And here in CNN, we have three different types of layers: convolution layer, pooling, and fully connected layer, right? So in front of you, this is like one architecture, linear architecture, and in this architecture, linear architecture, we have 5 layers, right? One, two. We don't count pooling as a layer, like so 1, 2, and 3, 4. This is flattened 4, 5. So let me count again: 1, 2, 3, 4, 5. This is the flatten operation, so we can ignore this one. So we have 5 layers in this linear architecture, and in this architecture, what we have convolution layer. This is convolution layer. This is pooling. Why we don't count it? Because like there are no parameters in pooling layer. We don't train the parameters of pooling layer. So whatever parameters we are counting, whatever parameters we are training, we count only those. So this is convolution layer. This is also convolution, and this is pooling. This is pooling. Then this is convolution. This fully connected one, and here also fully connected, and here also fully connected. Right. So we will discuss about all these layers one by one. Right. So first convolution layer, second convolution layer, and we have fully connected layers. Now here we'll discuss all these 3 layers one by one. So let's start with the convolution layer. I will come back to this figure because I need to explain you how we are like getting from input to this particular part, right? So first I will explain the convolution layer, then I will come back. So before that, let's see the generalized architecture of CNN. Here like we have input image, and we apply this input to a convolution model, a convolution layer, for extracting the features. So after convolution layer, we apply the ReLU. The purpose of ReLU activation function is to activate a particular neuron to bring the generalizability in our model. We use the ReLU activation function. Then we apply the pooling layer. Pooling layer is used to reduce the complexity. So here, here we'll see the main difference. The purpose of convolution layer is to extract the features, and the purpose of pooling layer is to reduce the complexity. When we train any of the model, then the weights of convolution layer will be changed, will be updated, but the weights of pooling layer will not be updated. These are fixed. That means we are not training the pooling layer, just we are training the convolution layer. That's why in a previous example we did not count pooling as a layer. Like you might have a question why we are taking like 2 sets or more than 2 sets of this convolution pooling. The reason is in the beginning just we extract the low level features. These low level features are extracted in the beginning. Then later on, like we merge all these low level features, right? And then later on, like in upcoming slides, these low level features become the high level features slowly. Low level features here means like just we extract pixel value, little bit age value. So we are not able to identify the object clearly from that low level features. So to clearly identify the object from that particular image, we should have a high level features. So high level features comes after several combinations of convolution and pooling, convolution pooling like that, right? So that's why it's a dot dot dot. We don't know how many set of convolution pooling we need to use. It depends on your data set. If data set is highly complex, then we might need like more number of convolution pooling. If data set is simple, then less number of convolution pooling can work. Now, after getting sufficient features, after getting sufficient two-dimension features, then what we need to do? We need to apply the flatten operation. So what flatten operation will do? Flatten operation will convert the two-dimensional features to one dimension. So for example, we have two-dimension features like this: 4, 8, 1, 20, right? 18, 255, like that. We have two-dimension feature, extracted features. Then we will convert these two-dimension features to one dimension with the help of flatten operation. So how it will be? Like, it's very simple: 4, 8, 1, 20, 18, 255, like that. Okay. So simple way, and this is the flatten operation. We can say this is a flatten operation. Okay, so once we get that flatten up, once we get the one-dimensional matrix, then easily we can apply the fully connected layer. So why we did all these things? Because for fully connected layer, we need input in the one-dimension format. So once we got the one-dimension format input, then we can just apply the fully connected layers. So how many layers we need to take? It also depends on our data set setup. And after this, in the last layer, we have a neuron. Here in these layers, like we can have a neuron on the basis of our experience based on data set. But in the last layer, the number of neurons will be equivalent to the number of classes, right? If there are multi-class classification problem, like for example, there are 10 classes in this data set, we need to classify 10 different types of vehicles: car, truck, van, bicycle, like that. Then we should have exactly 10 number of neurons here. We should have exactly 10 number of neurons here, and correspond and we apply the softmax function on the last layer. So what softmax function do? It generates the probability corresponding to each of the class. So H, there are like in input there are car, right? There is a car. So for car, it will generate the highest probability. Let's say for car, it will generate 0.6 probability, 0.6. Then the turn of truck will come. The features of truck. Few features of truck are similar to car, like there are 4 wheels, there is steering, although the size of wheels and size of steering is different than car, but there are 4 wheels, 4 steering. Size of truck is bit larger than car and all those things. So for truck also, like it will generate the probability, let's say 0.1. Similarly for van is also like similar to car, little bit difference is there, 0.1. But bicycle is completely different. Bicycle is completely different than car, because in car we have 4 wheels and body and all those things, but in bicycle we have only 2 wheels, and steering of bicycle is different, and most of the things are different. So for bicycle, the probability will be very low, like 0.001, like that. Okay, so now we'll see like the maximum probability. Where is the maximum probability? So for car, it will be maximum probability. Then we can say in this image there's a car. So in this way, like our deep learning model classify different types of images, and it produce the output. Now, now we will understand the convolution operation in CNN. Like we need this convolution. So how we apply the convolution on image data set? So for example, like you have this 8 cross 7 cross 7 image, and in this 7 cross 7 image, like we are applying this filter. And this filter, once we apply the filter, this filter will overlap like this, right? So the first point should be in the center. Like we are going to start, so it should be center, and element by element we multiply, like 0 multiplied by 4 plus 0 multiplied by 0 plus 0 multiplied by 0, like that. Element by element we do a multiplication, and then we add all these terms After addition, whatever answer will get like -8, that center pixel will be replaced by -8, right? Then we drag this window like left to right, top to bottom, and we get this particular output. So in this way, we can get an idea. And here, like if you see the complete convolution layer in detail, then here we can see the like particular setup. So for example, there are 5. Our input size is 5 cross 5. Their input size 5 cross 5, right? Here I will tell you why I'm telling 5 cross 5. This is this light blue color is the input image part, and this image is RGB, red, green, blue. There are 3 channels, and as I told you, like this is a 5 cross 5 image. I will explain later on like why I'm telling this 5 cross 5. It's 5 cross 5. Each channel we have 5 cross 5 setup. There's one condition here for convolution layer. If there are 3 channels in an input, like there are 3 channels in input, then in a filter also there should be 3 channels. 1, 2, 3. Right? It should be equal. At this moment, you can forget about this part. So we have 3 channels in a filter, and what will happen? Each of that channel, each of the filter channel will overlap on that image part. This will overlap on this one, this will overlap on this part, this will overlap on this part, like this. Now, if you are overlapping here, then how to do that? As I told you, we have 5 cross 5 image. So we are starting that image part from this position. We are starting from this position. That means we'll work on that pixel value. If we work on that pixel value, then this pixel value should be in center. This should be in center. That means we will have like this part. We'll overlap the filter like this. Now I think you understood why I told 5 cross 5. Because if we don't have these pixel values, like these values, side values, then it will like our operation will produce an error because we don't have these pixel values. So to make our calculation easy and to make our calculation error free, we add one extra bit of padding. Surrounding to that particular image data set. So here, like we have taken this pixel in the center and we added one extra bit padding to the image. And this bit of padding, like extra bit of padding, can be any digit. Like it can be 0, it can be 255, or it can be replicated. Like 0 is here, write 0, 0 is here, write 0, 1 is here, write 1. Why? That the reason is in real life the image size is very large, right? 256 cross 256, 500 cross 500, like that. So in that case, if we are going to include one pixel value, right, 500 cross 500 image there, and we are going to include one pixel value, then it will not impact much, right? Just corner pixel value will change a little bit, right? So that does not matter, but it makes our calculation easy. That's the reason we add one bit padding surrounding that particular pixel location. Now, once we added the padding part, and once we overlap that filter part, then we will apply this thing, right? We will apply this thing on that one. So now, element by element, we do multiplication. So 0 multiplied by -1. 0 multiplied by 0, 0 multiplied by 1, like that we'll do. So in this case, we'll get, if we'll do the 0 multiplied by -1, we'll get 0, right? Then again, 0 multiplied by 0, we'll get 0. Similarly, like for every 0, we'll get 0. So we just look on like non-zero part. So 1 multiplied by -1. So it will be -1. We are getting this one, so we get -1. So just we can write -1 here. Now again, I will apply on this part. This is in the center. Then we'll see this part here. Now element by element multiplication. So 0 multiplied by -1, 0, 0 multiplied by 0, 0, everything is 0. 2 multiplied by -1. So that means -2. 1 multiplied by 1 plus 1. 2 multiplied by 1 plus 2. 1 multiplied by 0, 0. So in this case, -2 plus 2 cancel out, we'll get 1. So we can write 1 here. Then similarly, we'll calculate for this part. And here we see this part like this. And element by element, again multiplication with this part. So here we can neglect the 0 part, just non-zero part. So 2 multiplied by 1 is +2. And then 1 multiplied by 0. So 0, either you can write or you can ignore, no problem. And then 1 multiplied by -1, so it will be -1, and other part is 0, so we can take 1. So here there is a 1. Now we got 3 outputs, right? 3 output values. Then we have like one bias also. Why we are going to use bias? Bias used to adjust the values of output. So then we add all these 4 terms. Once we add all these 4 terms, this -1 plus 1 will cancel out, 1 plus 1, 2. So that's the reason we are getting 2 here, right? 2 output in this case. So now what we need to do, we completed the first step here. Now the next part, we need to move our we need to move that particular filter on that particular image. So by default, we need to go from this location to this part, right? But we can use higher value of stride. So in this case, we have a stride equal to 2. You can see by default stride value is 1, but here we are taking stride value, leave 1 row and 1 column. So if you are jumping here, that means our model will overlap like this, or model will overlap like this. Okay, now our model will overlap in this way. Now our model will overlap in this with the same procedure we apply this part, and similarly we can have here also. Similarly we can have here also, right? So in this way we can do, and this part and this part, right? So this is the way, like it will overlap and we get output, and it will produce an output like 3 cross 3 or like 3 cross 3 like that. Okay, so this procedure will be repeated from left to right, top to bottom, and at the end, like we'll get this complete matrix. So this matrix is nothing, the extracted features. These are the extracted features. Now what will happen, we calculated the filters features with the help of this particular filter W0. Now in the image there might be different types of features, right? So only one type of feature we extracted with the help of this matrix. In this matrix there might be different types of features. Different types of features means few features might be like, let's say in a simple term, let's understand, there might be horizontal edge or vertical edge. So we can consider like this filter is useful for horizontal edge detection. We are using another filter that is useful for vertical edge detection. So with the help of this filter, we can detect the horizontal edge. With the help of this filter, we can detect the vertical edge. In reality, here, like we are not detecting horizontal or vertical filters. Those are completely different, but just for assumption, like from first filter, we are detecting horizontal features, and from second filter, we are detecting the vertical features. So likewise, we can apply these on image, and we can generate this one. So here we'll get the horizontal features, and here we'll get the vertical features from the second filter, right? So in this way, we can perform an operation. And if we talk about the parameters, where we have stride 2, filters 2, channels 3, and padding equal to 1, and accordingly, like we can get the output from that particular part, right? So this is the basic mechanism of CNN, and the number of output size of CNN does not depends on number of channels. Like their number of channels are 3, but our number of outputs are 2, right? So we can say number of output depends on number of filters. Whatever number of filters you have, that many number of output will be generated, right? And one more important point in this case, like for example, we have an input size n, filter size f, then our output size will be n minus f plus 1 cross n minus f plus 1. This formula will be applicable when we have by default stride 1 and we have padding 0. So in this case, this formula will be applicable, stride 1 and padding 0. If we have some different value of stride padding, then this formula will change. It will be n plus 2p minus f divided by s plus 1, n plus 2p minus f divided by s plus 1. In case we don't have we have only by default stride, then this formula will change like this. Okay, so now if we come back to this diagram, and on this diagram we can see like we have n equal to 32, n equal to 32, and we have f equal to 5 in this case, f equal to 5. So here in this diagram we have padding 0, stride 1, means by default case. So our formula will be n minus f plus 1. N minus f plus 1 multiplied by same term n minus f plus 1. So let's calculate one dimension. So n equal to 32, f is 5, so 32 minus 5, 27 plus 1, 28. So that's the reason we are getting 28 plus 28 here. And here in this diagram we are applying 6 number of filters. So that's why we are getting 6 cross 28 cross 28. Just like here in this example, we applied 2 filters, W0, W1, we got 2 outputs. And in this diagram and in this architecture, we are applying 6 filters. That's why we are getting 6. So just to differentiate filters from the image size, we use @. So 6 cross 28 cross 28. So 6 means 1, 2, 3, 4, 5, 6 filters you can see in this image. Now we apply the pooling. Pooling we will understand later on, but after pooling again we apply the convolution layer. So this is the convolution layer. So in this case, n equal to 14, n equal to 14, f is 5. So n minus f plus 1, 14 minus 5 plus 1. So 14 minus 5, 9 plus 1, 10. So we are getting size 10 cross 10, and the number of filters are 16. So 16 cross 10 cross 10, we are getting as the output size, right? Then again, like we are applying pooling. So pooling we'll understand later on, and later on, then after that we apply the fully connected layers. So I hope you understood like how we can calculate like output size using convolution layer. Using convolution layer, how we can calculate the output size. Now this we did, and one more important point here, like how to calculate the number of parameters. So in CNN, the number of parameters depends on the filter size, not the image size. So here, like we have filters. In filter, like for example, how many elements are there? 9. 3 cross 3, 9. So 9 here, 9 here, 9 here, right? 27 plus 1 bias, so we have 28. Right? Similarly, we have 28 in this case. So total number of filters or total number of parameters, not filters, total number of parameters are 56, or we can say total number of weights are 56 in this small architecture. Similarly, if we have like 10 filters of size 3 cross 3, like similar to previous one, then we will have 28 multiplied with 10, right? 280 number of parameters. So in this way, like we can calculate the number of parameters from any of the architectures, any of the deep learning architectures. Now after CNN, if we go back to that particular diagram, then we can say we have activation function like ReLU. We applied ReLU here. It is not necessary we need to apply ReLU always. We can use the different activation function also. So like let's discuss about different types of activation function. Here like we have sigmoid, tan, hyperbolic, ReLU, leaky ReLU, max out, and ELU. So different activation functions have different purpose. So like for example, in output layer, if there is a binding classification, then we use sigmoid, tan, hyperbolic. And the problem of sigmoid, tan, hyperbolic is that like we should not apply this sigmoid, tan, hyperbolic in the hidden layers or in the after convolution, all those things. The reason is the range of these sigmoid and tan hyperbolic are between 0 to 1 or -1 to 1. So they produce the problem of exploding gradient or vanishing gradient. So this is the problem of vanishing gradient. So to reduce that vanishing gradient problem, the ReLU activation function came into the picture. And if you talk about the ReLU, then it's maximum 0, x. That means here, if the value is positive, then it will come x only, like if this is x-axis, and if value is negative, then it will be 0. So in this case, we can apply the ReLU. Then we have a leaky ReLU, max out, and ELU. Like that, we can apply different activation function, nonlinear activation functions for producing the generalized output. Now, if we have like max pooling, pooling here means we need to reduce the size of the image, right? As I explained you earlier. So For example, we are going to use 4x4 filter size. We are using the filter size 4x4. If we'll apply the max pooling, then we'll take maximum out of these 4x4. We'll take the maximum out of this 4x4. So here the maximum is 9, so we can take the 9. Now, another example is 2x2 max pooling non-overlapping. So it is we can say interesting and the most useful. Mostly like we use this one only. So for that purpose, we select 2x2 window. We take maximum out of these 5. Again, we take the maximum 2x2 window. We select maximum out of this 6. Like that, we select all these values 8, and here we select 9. Like that, we can use this 2x2 max pooling overlap non-overlapping, and here overlapping part will come. So for overlapping purpose, what we can do, we'll erase. Then for overlapping purpose, just we'll overlap like a statical to 1, right? So in this way we'll go. So we'll overlap. We'll take the 3 values, so 5, 5, 6. So now it is not always necessary that we need to apply max pooling. We can apply min pooling, average pooling, median pooling. Based on the requirement, we can apply like different things, but max pooling is like most popular. After that pooling, okay, so let me go back to that diagram to explain you about the pooling layer. So here, like in this diagram, we have 28 cross 28 is the output size from convolution. Then once we apply the pooling 2x2 non-overlapping, then 28 will become half, 14 plus 14, and the pooling layer does not change number of filters. So number of filters will be same. So we'll get 6 cross 14 cross 14, just half of that image size. Again, here also we are applying. So 10 cross 10 will become 5 cross 5, and number of filters will not be changed, 16 cross 5 cross 5. Okay, so this is the way like we can work on, and here we can see, and here also like we converted that 4 cross 4 to 2 cross 2 and a half. So this one is the most popular one, 2 cross 2 maximum max pooling non-overlapping one, right? So it makes the size half, like whatever image size you will give, it will produce in the half size. Now next layer is the fully connected layer. So before fully connected layer, like we flattened, then like connected all neurons fully, and these are connected with the different weights. So we need to train these weights value, and in the last layer we assign the classes. So if there are 3 classes, then we need to do the 3 class one, and we use the softmax activation function. So this is the way like we work on, and then if you see, like I already told you, we apply softmax, so we can ignore this slide. And there are different architectures are there for CNN. Now, here, like we discuss about the CNN, convolutional neural network, and CNN is very popular. We use like researchers use this CNN for different application purpose. But whenever we talk about medical imaging, then in medical domain, like in most of the cases, the CNN can't produce the accurate output, right? So for example, like we are segmenting something like knee MRI or something. So if we need precise output, then we need to extend or enhance our model, CNN model. So here in front of you, there is a unit model. This is the extended version of CNN. The shape of this model is just like U, right? And here we also use the same difference level with image, like where like channel is 1. Then we apply CNN, convolution layer with filter size 3 cross 3 and value activation function. Once we apply 3 cross 3 filter size on top of this, then in this case n equal to 572, right? N equal to 572 and f is 3, right? So n is 572. So if we apply the formula earlier, like we learned one formula, n minus f plus 1. If we apply this formula, then 572 minus 3 plus 1 will do, then we'll get 570. So that's the reason we're getting image size 570 cross 570. And in this case, we are applying 64 number of filters. 64 number of filters we are applying. That's the reason we are getting output size 570 cross 570 cross 64. That's similar way like we explained earlier, like we used 2 filters W0, W1, we got output size in a 2, right? So here we got 570 cross 570 cross 64. Again, we are applying max pooling, convolution, and in this case, the input n equal to 570, f equal to 3, then we'll get 568, and filter size 64. After that, we apply the pooling operation, max pooling operation. Here you can refer from here 2 cross 2. So what pooling operation do? It makes the size half. So 568 will become 284. So we get 284 cross 284, right? 284 cross 284 size we will get. Then we apply. Then what we need to do? We then again we apply the convolution operation just like this one, and convolution operation again, then pooling. So this process will be repeated for several times, right? For several times it will be repeated. So this part is called encoder. This part is called encoder, right? This part is called encoder. Here, like from 572 to 572, we got 30 cross 30 or 28 cross 28. So here, like we reduce the image size a lot. Like this architecture believes, like we got very high confidence feature, in this case. Obviously, we got very high confidence feature, but one problem we can see, we reduce the size from 572 to 30 cross 30 or 28 cross 28. This is a huge problem. So what we need to do? We need to go back. We need to reverse back to the original image size, right? We need to reverse back on original image size. That we can do with the help of up-convolution operation. So what up-convolution operation will do? It will make the size double. Like 28 cross 28 will become 56 cross 56, like that. Okay, so we'll repeat that. Now, one more important point here we can see. The important point is we went from encoder to decoder. This part is called decoder, right side, and left part is called encoder. We went from encoder to decoder. It might possible like from encoder to decoder, like earlier, like image size by 572 cross 570. Here we got just 30 cross 30, 28 cross 28. It might possible like we might have lost some important features, right? Because we reduced the image size a lot. So to preserve all these features, we use skip connections. So for each level, we are going to add skip connections from left to right. Skip connection here means just we'll take half of the part and we'll copy here. Half of the part will take copy here. Half of the part will take copy here. So this in this way, like we apply the unit, and from left to right we do, and we can find the output, right? So this is the way like we can do, and this is like mostly we use this unit for segmentation purpose. So if you are segmenting any of the like image by like medical image or something, then that means we are dividing image mainly in the two parts, right? Foreground and background. That's the reason there are two here to classify in the two different classes. As I told you, we can use softmax activation function, right? And it will reduce the probability corresponding to each of the class. So for all these two classes, like probability will be produced by the segmentation function, right? So we can use this this CNN and all this deep learning in many different application areas like MRI and CT scan. So like it can reduce the number of unnecessary exam, reduce number of misdetection. We can use this one for diabetic retinotherapy detection, tumor detection from MRI, CT, X-rays, skin lesion classification, ultrasound classification, right? For many other different purpose, we can use this like in different biomedical environment. We can compute the we can highlight the region of interest, we can compute the volume, surgery planning, and all those things we can do with the help of image data set, right? So many things we can do with the help of this image data set, right? We can segment image into different parts using biomedical applications. Now what I'm going to do, I'm going to discuss one of my work where like we applied these unit architectures, different unit architectures we applied in a 3D on the 3D MRI image, right? We segmented these 3D images in different cartilages, like we segmented the cartilage in different parts. So for this work purpose, we applied like we used three data sets: OAI, CCBR, and LIRA. OAI data set is publicly available, but CCBR and LIRA both are private data sets. And for this work purpose, we collaborated with radiologists in Copenhagen Hospital, Denmark, and radiologist only provided this particular data set, and they produced this data set by Copenhagen patients, all those things. So real world data set was huge, and our method was completely validated validated by radiologists, right? And they provided the input to us, like what we should do, and they validated the result in different environment and for different conditions, right? So to understand this work, let's directly go on this block diagram. And in this block diagram, you can see on the left hand side we have MRI image, 3D knee MRI image, 3D scan, and this is the OAI data set. This is the OAI data set. 3D image is there, OAI data set. From this data set, we extract the slices, right? From different directions, we extract the slices. So for that purpose, we are using multiplanar. Multiplanar means from different planes, we extract the slices. From different angles, we extract the slices. So if you're talking about the angles, then in this case, we are keeping the difference of angles at least 60 degree. Although like we generated those angles randomly, but here we kept the difference 60 degree. Now, first of all, try to understand. Let's understand the difference between like scan and slices, right? So here I would like to show you one thing, like you know the loaf of bread, right? Loaf of bread. So let's see. If you see the image of loaf of bread, then this is the loaf of bread, right? This is the 3-dimensional structure, right? Loaf of bread is 3-dimensional structure. Now, out of this loaf of bread, what we need to do from this 3-dimensional structure, we need to extract the slices, right? 2-dimensional slices we need to extract from this 3-dimensional structure. So for that purpose, what we'll do, we will like chop up, right? We will chop up this particular 3-dimension like a structure. Let me take it in the full screen. For example, this is 3-dimension. Now, by taking knife, we'll chop up this one. So we can chop up this from different directions, from different directions, right? So likewise, same thing we did for our case. Like we have a 3D scan, 3D MRI scan like this, and we chopped that 3D scan into several 2D slices. So once we chopped into several 2D slices, we'll get image like this, right? 2-dimensional images like this, okay? 2-dimensional images like this. So these 2-dimensional images are called slices, and 3-dimensional image is called scan. So what we did here, we we have taken this scan 3-dimensional image. From that 3-dimension, we chopped that 2-dimensional slices from different angles, and these angles were generated randomly, but we try to keep the 60-degree difference. So, like why we have taken 6? Because we want to cover total 360, right? And now, after extracting these slices, we kept it one place, at one place. Then kept at one place. Then we applied a unit 2 plus. Here we applied a different variants of unit. Like we applied unit 2 plus, unit 3 plus, unit 2 plus deep supervised version, unit 3 plus deep supervised version. So 5 different variants of unit we applied. I will show you those variants in next slide. And then unit 2 plus produced the very high accuracy in our case. So that's the reason we are focusing on unit 2 plus here. And in this case, we have input size W cross H cross CH, means width, height, number of channel. So if there's a color image, then channel will be 3. If it's a grayscale, then channel will be 1. And the output size is W cross H cross K, width, height, number of classes, right? So this is the OAI data set. OAI data set. In this data set, there are 7 classes. There are 7 classes, right? So here we got the segmented output. And in this segmented output, you can see the 7 different colors. These colors are nothing but just the generated probability from softmax activation function. As I explained you earlier, in the last layer, if we have multi-class classification problem, then we apply the softmax activation function. So what softmax activation function do? It generates a probability corresponding to each of the class. So these are the generated probability. We plotted, we colored each different types of probability with different color, right? So we got the segmented output corresponding to each of the part, right? Each of the part like that. Then here, the like one issue might be there, like it is not necessary that we'll get the output in this format because we extracted slices from different angles. So definitely our output will not be in this format. So to make the output in this format, we apply the nearest neighbor interpolation, right? We apply nearest neighbor interpolation. By interpolation, we got the output in this format, and this output is not the proper 3D, right? Proper 3D, because we extracted slices. To make it proper 3D, we again do apply the fusion model, and that fusion model was applied with the help of artificial neural network, right? So we use artificial neural network, and using this artificial neural network, we fuse and we got the output. So here input size is v cross k, means number of planes and number of classes. The output size is number of classes format. We got a scan, and in this scan we are getting 7 different classes, right? So this is the way we work on, and we can like apply this multiplanar unit model for different purpose. Here we tested this approach for different variants of unit, as I mentioned you, as well as we tested this method for different number of planes also. See here I showed you 6 planes, but we tested it for 1 plane only, and 3 planes and 6 planes, right? But we for illustration purpose is shown, like from different angles we extracted the planes, and this is one direction, and here like all direction, all planes, like that. Okay, now for calculating the accuracy, we apply the fusion model. So for fusion purpose, what we did, we calculated all these 6 views, 6 planes, then we fused all these 6, we got the predicted output, we got the 2 output, then we compared the 2 output to predicted output, and we compared the dice score, and we got the dice score again. Okay, so this is the way like we did, and we produced if like this true accuracy is matched with the predicted accuracy, like then dice score will be high. So yeah, accordingly we calculated dice score, and like that dice score defines the like quality or like accuracy of that model. So now if we talk about the unit model architecture, then here like we have unit simple. That I already explained you. We have encoder, decoder, and like escape connections, just like previous one, only just we changed that like structure a little bit, right? It's similar to previous one. Now this is the unit 2 plus advance of unit. Here in unit 2 plus we have encoder, we have decoder, as well as we have medium coder, right? So the purpose, the target of unit 2 plus is to preserve, to like preserve all the features. Like it is used for full scale skip connections. It is used like we call that like full scale skip connections. That means we are using these full scale skip connections for preserving almost all the features. Here we believe like even with the skip connections we might have lost some features, but here we believe we have preserved all the features, right? So this is unit. In the same way, like in literature, unit 3 plus was also claiming that we are better than unit 2 plus. So we thought like, well, like let's test this approach on the unit 3 plus. So in this case, like it's similar to unit 2 plus only, but the connections are different in this way, right? And in unit 2 plus we get output from this part, and unit 3 plus we get output from this part. But if there are 2 more different versions, unit 2 plus deep supervised version, in deep supervised version we got output from these 4 parts. Then once we get the output, then we apply the then we apply, not able to use pen. So then we apply the something. Then we apply the maximum likelihood here, right? And using that maximum likelihood, we get the output. And similarly here also, like we get the output from these 4 nodes, and then on this, using this output, we apply the maximum likelihood, then we get the output, right? So this is the way like we apply unit 2 plus and unit 3 plus, and then like we tested these approaches for one model, but in our case just simple basic unit 2 plus produce very good accuracy, so we could focus on that part only. So here like we see understanding mathematically, we already like I already told you x like belongs to r w cross h cross ch with height channel, and w cross h cross k, where like k is the number of classes we have, right? So segmented output we are getting. So his segmented output means like here we can see segmented output. So this is S1, segmentation 1, segmentation 2, segmentation 3, like that. Okay, till X6 we can get. And so we are getting like S, where S equal to SV, V will belongs to 1 to 6. Okay, so V value will vary from 1 to 6. V1 V equal to 1 to 6. So because we have 6 planes, so S1 to S6 will get this point here. Now, for fusion purpose, we apply the neural network I introduced. This is the objective function for neural network. And here, what we use, the input will be considered as a probability that we generated from software function in the last step. And we are just apply the random weights and biases, and then we train this model. So PKXC is the probability of class C at voxel X predicted by segmented SK. Right, so this is a probability, and we are applying weight, and we are applying the biases, and we are going to run. So this is the way like we can work on, and we can train the model, and we can get the final like accuracy. Now this model was tested as I already mentioned on 3 data set: OAI, CCBA, and Lyra. And number of scans we'll talk. Then in OAI we have 60, CCBA we have 140, in Lyra we have 39 scans, and number of slices like extracted 2D slices, and then in OAI, we have 7 classes. You can see medial TVL, lateral TVL, all those. Then CCVR, we have 2, and in Lyra, we have 5 classes. And these are other parameters we received from a radiologist, like scanner and all those things, right? Then we're using these parameters. We calculated the DICE score. We did the performance comparison with the help of DICE score for this segmentation problem. And like here you can see the results for OAI with 7 classes, CCBR with 2 classes, Lyra with 5 classes, and number of parameters also, right? So in this way, like we calculated, and these are the number of hours we took, like 93 hours, 26 hours, 47 hours for like training time for this particular model. So our method performed significantly better than like others, but like in few cases we identified like method is not performing in a like very good way. So for what we thought, we tried to then we thought to apply the pair t test for like a pair wide comparison purpose, and this pair t test was applied with 5% level of significance, means we compare the value with 0.05 because 5% level of significance. And to prove that like our method is performing significantly better than others, then our alternative hypothesis should be true and null hypothesis would fail. So when alternative hypothesis should be true, then in that case, like the value of this particular t-test should be less than 0.05, right? 0.05. So in most of the cases, it's a little less than 0.05, except this case and this one, right? But in most of the cases, it is like very far less than the 0.05. So we prove like our method like performs significantly better than others. Now to prove the performance, generalized performance, what we did, we plotted the box and whisker plot. So actually we want to prove that our method can perform in general case. That means if if we apply any unknown data set to our model, right? Some other data set, unknown data set, related unknown data set like need segmentation, some other data set, 4th or 5th data set, like we apply from downloading from public or private data set, then also our method should work better. So for that purpose, what we did, whatever 3 cohorts we had, like OAI, CCBR, and Lyra, we combined all the DICE scores of these cohorts. So we combined class-wise. So if you see, in this case, the data set characteristics, in this case, like the 2 classes, medial TBL and medial femoral, right? These 2 classes are common in all these 3 data sets. These 2 classes are common in all these 3 data sets. So what we did, we combined DICE score for medial TBL from all these 3 cohorts. We combined DICE score of medial femoral from all these 3 cohorts. After combining these DICE scores, what we did, we plotted the box and whisker plot. So here you can see the box and whisker plot, and box and whisker plot for medial TBL, and just for medial TBL for MPUNet and MPUNet 2+, and for medial femoral for MPUNet, MPUNet 2+. So here, if you don't know the box and whisker plot, it represents like 100 percentile, 75 percentile, 50 percentile, and 25 percentile. This is mean, this is median, and these are the outliers, right? In a similar way. So if you want to compare, then you need to compare this one to this part, and this one to this part, because this one is a medial tibial and here is a medial femoral. So if you compare, then here we can say our method performs significantly better than the others, like median is high, mean is high, we have less number of outliers and all those things. So in general case also, like, method performs better. Now these are the like statistical information from box and whisker plot, the mean, median, maximum, and all those things we extracted. So I'm not going to discuss this thing. Now what we did, like sometimes what happened, a particular class performs very good, right? A particular class performs very good, but like few other classes, like sometimes the other class does not perform better, in a better way. So what we need to do, like what we did, we compared, right? We checked the accuracy class wise. For each class we checked the accuracy, like for like in AI we have 7 classes. So for all 7 classes individually we calculated the accuracy dice score, and then for CCVR 2 classes, in lyra 5 classes we calculated, right? And then we have seen this part, and now in all cases we can say our dice scores like perform very good. In such kinds of data set, if we are getting dice score more than 0.8, that means it's very good. So it was a very complex data set. So class wise also, like, our method performed very well, right? We got very good accuracy. Now we did lots of quantitative evaluation, but without qualitative evaluation, like our study will not be complete, because until unless we not see the visualized result, it is very difficult to believe that thing. So for that purpose we did qualitative evaluation also. For qualitative evaluation, what we did, we have taken input, right? Ground truth, like this is the ground truth, and we plotted the result corresponding to each of the graph, right? So here we can see this is our method and these are the other existing ones. So clearly you can see our method performs similar to the ground truth, except like there are some problems. So here you can see like there's some problem, but it is still better than others. You can see others like there's a major problem. So like we got better qualitative results. Now here these are the qualitative results from individual things, like these are results from this part. I showed you this thing where these are results from this part, right? This one. So these are not the complete 3D image. So as we have given input as a 3-dimension, so we want our comparison in terms of 3-dimension image. But it is very difficult to visualize the 3D image. It is very difficult to visualize the 3D image. So what we did, we applied some trick to visualize the 3D image on 2-dimension plane. What we did, we did the projection. We did the projection of 3-dimension image on 2-dimension plane, and we did the projection for false positive and false negative. We did the projection for false positive and false negative on 2-dimension plane. And now each of the cartilage, medial femoral, lateral tibial, lateral femoral, like that, and for all the data sets, OAI, CCBR, and lyra. So now if you compare, then if you see, this is the 3D projection for MPUNet, this is 3D projection for MPUNet 2+. There is a minor difference. There is not like a such major difference, but the minor difference is there, and here we can see that part, right? So this is the way like we can work on, and we can get the part, this one, right? So we can do this thing, and likewise, like we did the projection, and we did the comparison from like false negative part, right? So here like false negative, here you can see the yellow part, like little light yellow. Here it's a real dark yellow. The dark yellow means we have large number of false positive, large number of false negative, like that. Here also like we have similar thing, false positive. Here, like here, you can see the clear difference. Here dark yellow, here light yellow. So dark yellow means we have large number of false positive or false negative, right? So likewise we compare for all the cohorts and for all the data sets, and then we in most of the cases we performed well, better than the others one. So now to conclude this work, like we propose a generalized multi-tenor full-scale connected unit model, and we use 1, 3, and 6 number of planes, and total number of slices were used, like 30,400 number of slices were used. And for this work purpose, like the LIRA data set was used first time, right? Before our like published paper, like no paper was available on LIRA data sets, right? Now there might be a few other papers, but at that time no paper was available, and we did extensive quantitative and qualitative evaluation for different purpose, and we got the result. So this is about the work related to this NIMRI segmentation, and there are some other works are also there, right? Other works are also there, but like due to time, like I'm not able to like explain all this. So it's a time for questions. If you have any question, please let me know. I hope like few questions might be there in chat box. So let me see.
Sir, since it's YouTube live, questions have been posted in YouTube, and I have put all the message in the chat.
Chat, huh? So
Yes, sir.
I can't see. Just only one question is there.
In MS Teams, I have given many chats, sir.
Just only one question I can see. Jaspreet Singh, can we use AI with CT scan machine? What is CT scan? CT scan, it should be CT scan, right? CT scan, computed tomography machine. Yes, we can use AI there with CT scan. People are working on that. It's one of the good area, like CT scan, computed tomography machine. So here, like what happened, this is a major problem in radiologist. Like for example, one radiologist has like CT scan machine of different company, different makeup, and another like a radiologist have a different mix. So if we go for CT scan with one machine, and we'll go for another machine, that sometimes there might be difference from one CT scan to another CT scan. So for that purpose, nowadays like people are using generative AI for like aligning the scan from aligning the scan from one machine to another machine. So we can use AI in CT scan machine also. So this is one of the very good area at the hardware level. People are like applying this one. Okay, so next is for segmentation, which type image more suitable? Color, gray, and gray. It depends. It depends. So it depends on your data set, complexity of like data set. Sometimes color image, grayscale image. It depends on the type of data set for what purpose like you are going to use. So we can't give a clear answer which image are like more useful. You can use color image also, grayscale image also, but obviously like color image will be better, but it will leads to a high computational complexity. Now next is, does CNN work only on image or also for text and numerical data? Mostly CNN is useful for image data set, and if you can convert text or numerical data into image format, then we can apply CNN. But for text part, we can use one dimension CNN, right? But most popular are the like 2 dimension or 3 dimension CNN. Can you please explain 2D and 3D in CNN? Yeah, so 2 dimension CNN means just we use that 2 dimension matrix filters, 2 dimension filters. But in case of 3 dimension CNN, in place of 2D filter, we will use 3D filter. Like we will use depth also in the filter, so that will be 3 dimension. But the 3 dimension CNN is highly complex than like 2 dimension, because we have lots of parameters in 3 dimension one. So this is a basic difference between CNN, 2D and 3D. In 3D CNN, we have three filters in the 3 dimension part. So width, height, and depth. How to determine upsampling or downsampling? So like upsampling and downsampling related to like pooling here we are talking for, right? So here like we selected the part like complete image, and we apply the pooling, and we got the smaller part. And in a similar way, like we can do the reverse operation of pooling also. That can be the like upsampling, and like if you are applying pooling, that may be the downsampling. So in this way, like we can take the part of image with the help of sampling operation. Now next is, where will I find just have to predict heart stroke. You can like try with different like website. UCI repository is there, and kegels are not there. Kegels are there, but like people like sometimes don't believe on kegel. Like some ethical issues is there related to kegel. So some UCI repositories are there. Some repository are there on Stanford University's website also. So just try to take out there. You can find it. Purpose of fusion model. So here, like we applied the fusion model because earlier, like we extracted like whatever segmented output we got. But that was not the proper segmented output. Proper 3D segmented output. So to make it 3D, we fused all those segmented layers. So that's why we applied the fusion to make the 3D output, because we have given the 3D input, we want the 3D output. How do we generate a small language model for having minimal data set of music notes for the recognition and prediction? So it depends on your like data set, like what kinds of data set you have. I don't have that much idea about the music, but like as I understand, this is the one dimension like data set, and mostly like you should avoid CNN for that purpose, but you should prefer some other, right? So I don't have much idea about that thing. Which is better, unit 2 plus or unit 3 plus? It's depend. Like in literature, unit 3 plus was claiming better than unit 2 plus, but in our case, unit 2 plus was better, right? So like just we will tell, I will tell like unit 2 plus is better. How does encoder decoder structure affect feature extraction? So feature extraction part, like here we are trying to extract highly confidence feature with the high confidence feature with the help of encoder. The purpose of encoder is to contextualize representation of information. Like contextualize representation of information we are doing with the help of encoder. So we are representing the most important information with the help of encoder, and the purpose of decoder is to reconstruct that information part, right? So in this way, encoder decoder go on to predict or identify symptoms of heart attack. Priority, which model can do best? Where can we find that kinds of data set? So just you need to search out the data set. For a specific purpose, I can't tell like where you will get the heart attack and all those data set. There are some as I said earlier, like UCI and other repository are there. So just you need to search over there. And which model, like mostly like CNN, and like you can apply unit also for that purpose. These free data set? No, these are not free data set. Only OAI is the free data set, open source. Other are not free. How does batch size affects training conversion? So if you have batch size, so like training will converge bit fast, right? Depends on batch size. Whatever size of batches are there, like training will be fast. And if you have like larger batch size, then training will be slower. So to reduce the GPU, like to use GPU effectively, we use the batch size. Free data sets, volume IDC data set. I don't have any idea about that. Generate the data set and use it. You can generate a data set if you have CT scan machine, X-ray, MRI machine, then you can generate a data set. Any free data set available. You can find the data set link from my one of the paper. Just search my profile. You can find that paper. In that paper, the data set link for OAI is given. But as I mentioned, CCBR and Lyra are private, so there is no link is provided. Data set. Just see my paper for see the website. So in V2 transfer, well, like people are going out of context. What about DIET, defense, DBN is DBN is deep belief network, DSN is deep stacking network. So in deep stacking network, what we do, we have different types of architectures. We combine these architectures, different architectures to get the very good accuracy. That's deep stacking network. Deep belief network is based on like old architectures. Earlier, like some belief, like some architectures were there, but they're like related to neural network. Then they extended that neural network architecture. It was not exactly neural network, like neural network only in a rotated way. And then they extended that architecture for, and they made other deep belief network, right? So we don't have a time to go in detail how we select the filter. Yeah.
Sandeep sir?
Yes, madam.
Yes, sir. Yes, sir. Sir, you have been answering for all the questions. It's been very happy to have a person like you. So
Yeah,
we'll be
madam.
happy that if you share your PPT with us.
I already shared. I already
Yeah,
shared with the Dr. Praveen, so you can collect it.
yeah, I will check, sir.
Yeah.
So it's my privilege to thank today's speaker, enlightening speaker of the FDP session on deep learning. I extend a heartfelt gratitude to Dr. Sandeep Singh, senior lecturer at Cardiff Metropolitan University, UK, for sharing his expertise with us. His lucid explanations, in-depth insights, and practical perspectives on the applications of deep learning have truly enriched our understanding and sparked new ideas of research. With this, I conclude today's session on the note of gratitude and inspiration, looking forward to many more such knowledge sharing interactions with you in future, sir. Thank you, Sandeep, sir.
Thank you, madam.
Thank you.
Yeah.
Thank you, sir.
Thank you, madam. I'll leave it now. Thank you. Bye. Bye,
Thank you.
everyone.
Good evening to one and all. Welcome to day 3, session 6 with Dr. Nikhil Tripathi. Welcome you, sir.
Yeah,
Nikhil, sir?
good evening
Yeah,
and thank you,
yeah,
Professor Vani. Please let me know
yeah.
if you can hear me properly.
Yes, sir. You're audible, sir. Just give me 2
Okay,
seconds, sir,
perfect. Thank you.
for introducing.
Sure, no problem. Yeah.
It's my privilege to introduce our guest of the day today of session 6. Dr. Nikhil Tripathi is an assistant professor in Department of Computer Science Engineering in IIT ISM Dhanbad. He joined IIT Dhanbad in December 2024. Before this, he held positions as an assistant professor in IIIT Sri City and SOA University, Bhubaneswar. He worked as a postdoctoral security researcher in Fraunhofer Institute for Secure Information Technology, SIT Germany, and has a PhD in computer science engineering from IIT Indore. He has over more than 10 years of experience in vulnerability assessment of application layers, protocols, and developing defense mechanisms. His research interests include network security, system security, computer networks, intelligent transportation systems, and cybersecurity. He has published research papers in reputed journals and conferences and also holds a common vulnerabilities and exposures CVE entry for and vulnerability in NTP protocol. He is actively involved in teaching courses related to computer networks, data structures and algorithms, and web services. Outside academia, he enjoys music, traveling, motorbiking, and complete history studies. Welcome you, sir. Sir? Nikhil, sir? So you are not
Yeah,
audible.
sorry. I my microphone. Yes. Is it audible now?
Yes, sir. Welcome you, sir.
Okay. Thank you very much, Professor Vani, for the warm welcome. And I'm extremely delighted to have this opportunity to present one of my, research domain on which I recently started working. So, could you please confirm if you can see my screen?
Yes, sir. Screen is visible, sir.
Okay, perfect. Thank you. So basically, in this presentation, I will be covering a brief, overview of a research that I recently started working on, and this research is basically it falls on the intersection of machine learning and network security. Most of the part is from network security, but since again now
So
we
sorry
are
for
seeing
disturbing the sir.
yes,
Sorry for disturbing. The lecture is YouTube
yes,
live.
please.
The questions will be posted in the MS Teams chat then and there.
Okay, perfect.
Yeah.
Perfect.
Thank you, sir.
Fine, no problem. Yeah. Okay. So basically, as I mentioned, we this presentation will be on the intersection of AI as well as network security. My domain is particularly network security, and I will try to discuss why do we use machine learning in this network security domain, and that too for when we talk about encrypted IoT traffic. I mean encrypted network traffic. And by the way, please understand that this the domain will not is not restricted to IoT. I mean, this domain is open for the issues that we face in normal network traffic also. So when whatever we will discuss, that will be applicable not only to IoT traffic, but for other our normal daily network traffic as well. So with that, I will start the presentation. So as you can see, the topic for this session is AI, artificial intelligence for encrypted IoT traffic. So now again, we can have different modifications to this. We can have, we can have different ways of implementing different artificial intelligence algorithm. We can work on Gen AI. We can work on federated learning. Okay, so I believe all these are part of AI, and it's up to you depending on what problem you are trying to solve. Based on that, we can have different types of algorithm that you can use. Okay, so as I mentioned, we will be focusing more on the network security part and why do we need this AI component in that. Okay, so why to focus on encrypted IoT traffic? So there is some glitch, please ignore this. Okay, I think it is fine now. Okay, nowadays IoT devices, it is embedded in our daily life. IoT, basically, I am assuming that we are talking about right now smart devices, okay, which is not restricted to your mobile phones, I would say. Instead of that, we have smart refrigerators, smart washing machines, smart air conditioners, smart TVs are there, right? So now what happens when we have normal traditional devices in our homes? They are, we used to call them as dumb devices. They are dumb devices. Why? What is the reason? Because they cannot communicate with anyone else. If they are not able to communicate with anyone else, that means that they we can call them as dumb, right? But now as internet evolved, as the network research evolved, the development evolved overall, we got all these devices as smart because now they have this ability to communicate with other devices within the network or outside the network over internet, right? So that's why we call them as smart devices. Now the problem here is when they start communicating with each other. Let's say there is one smart speaker. The Echo Dot speaker or Google Home speaker and all that. We have this tendency to use them a lot, right, in our homes. So they can communicate with your smart bulbs, right, for proper lighting of your house. Then they can communicate with your smart televisions to whether to switch them on or switch them off, something like that. So while doing so, they generate a lot of traffic. Of course, when they communicate with each other, they do that with some sort of network traffic. Some traffic will be generated, and this traffic is not restricted to smart devices. It can be any device. It can be your pacemaker that is there in the heart patients, right? It can be your smart watches that we see everyone is using nowadays, right? So all these devices, they are generating some traffic, and that is used to communicate with other devices within the network or outside the network over internet, right? Now the problem here is when we talk about this network traffic, this is a big challenge. Problem here is this network traffic can be completely, this can be completely in clear text. The problem here is when we talk about clear text network traffic. So if we take this topology, let's say here is your one smart device, here is your another smart device, and both of them are trying to communicate with each other. Let's say with clear text traffic, anyone sitting here, it can capture the traffic. It can easily capture the traffic through attacks like MITM. What is MITM and all? It is very much specific to network security. So I will not go into those details. But MITM stands for basically man in the middle. And so we are assuming here that C is the man in the middle between A and B. Now what C is doing, whatever data A is sending to B, C is able to read that. Whatever data B is sending to A, C is able to read that. Now this is the problem. This tampers the privacy. Why privacy is gone? Why confidentiality is compromised? Because now this data what is being communicated, that is not restricted to only A and B. That is leaking to C as well. So this is the problem. So what researchers did, they came up with new approaches. Of course, we have cryptography, very famous research domain, right? Everywhere we see cryptography is being used nowadays, lightweight cryptography. Then if we have sufficient resource, then of course we can work on high-end cryptographic algorithms. Since we have cryptographic algorithms, we integrated cryptography into network. So we got cryptography plus network. Now what is this cryptography here? I hope quite a few of you are familiar with this. We have a lot of encryption and decryption. Encryption means we encrypt the data so that it is not in clear text. And in case let's take this same topology again. Let me remove this. Let's take the same topology. If let's say this is the case, again, both of them are trying to communicate, but now the data is encrypted. So let's say a tunnel is created here. Let's say a tunnel is there. Now, if this tunnel is encrypted, even if C captures the data, even if C captures the data here, C will not be able to understand what is going on between A and B. It will receive some random string X to A, B, question mark, P, exclamation, 239 X, P, something like this, some random string. So of course, C will not be able to understand what is actually going on between A and B. So this is how we can make sure the confidentiality is not compromised. How to do that? By simply integrating cryptography into the network. And that's why we have nowadays a lot of cryptography domain. I mean, the researchers, they are working on the intersection of cryptography as well as network. Nowadays, since we are focusing our discussion on IoT, so we can say this cryptography is being integrated into IoT devices as well. Only constraint is that these IoT devices, we all know that they have limited resource, limited battery power, right? So we cannot directly deploy any high-end cryptographic algorithm like our RSA, right? We cannot simply deploy them on these resource constrained devices. It will not work, right? I mean, even if it will work, the problem is it will consume a lot of battery power, it will consume a lot of processing, it will drain your RAM as well, right? So we have this restriction. So that's why in cryptography, we get some lightweight cryptographic algorithm like ECC. Again, ECC is not that lightweight, but it's still comparable to, if we compare that to RSA, that is much more lightweight, right? So like this, we have different cryptographic algorithms. So all the researchers who are working in cryptographic algorithm, they can answer this better. What are the types of cryptographic algorithms that we can deploy on IoT? And what was the purpose? To ensure that the data is encrypted so that no one else in between can compromise the confidentiality, right? So that's why we have everything encrypted now. Then we will see in this talk what is this problem that we are facing with the encrypted IoT traffic. What is the problem? If we have encrypted IoT traffic, then that means that life is sorted, right? I mean, confidentiality will not be compromised. Even if someone compromises the network, they will not understand what is going on between A and B. So what is the problem now? So that is the problem that we will see, and we will see why to use AI for that. Okay. Sensitive data transmit health metrics. So I gave one example of pacemaker. Pacemaker, I hope you all know. So it's a device, I guess. I mean, for all the health patients. I mean, heart patients, and they have this planted in their heart, and that is used for proper functioning of the heart, right? So like this, we have multiple health devices which are there. Then our wearable devices which people use to analyze their daily routine, daily workout, and all those things. So they have a lot of private information that should not be shared with anyone else, because then that will lead to data exposure, and then that will simply create a different problem altogether, right? So we don't want that. Surveillance. When we talk about CCTV cameras, earlier we have very simple CCTV cameras, right? They need just power. Okay, you simply plug them to the power source, and you can see the display on a television within your home. But now we have a smart CCTV camera which are connected to internet, right? Whatever they will capture, you can see the screen. Whatever they are capturing, you can see it anywhere in the world, right? You can be anywhere in the world, and you can simply see what is going on in your home, right? So they are much smarter. They can connect to the network. They can communicate with other devices, right? Then energy uses. So of course, this is something that should not be revealed to someone, because if you know that, let's say we talked about drone in defense areas, right? A lot of drones are being used in defense sector. If the adversary knows that, okay, this drone that we are getting right now, the drone which is launching the attack, if the energy is down, I mean, if the battery power is down, then no need to waste your missile or anti-drone missile on that, right? Simply you should not do that, because anyway that drone will go down because the energy is gone now. So no need to waste resource on that. So these are some examples of sensitive data. We should make sure that these things are not compromised. The confidentiality of this data is not compromised. Visibility gap. What is the importance of encryption? Other importance: encryption protects privacy but creates security blind spots. So this is what we will discuss in this presentation. We have AI for our rescue. AI solutions are there. Interpret behavioral metadata when payloads are unreadable. So let me discuss this. in a rough slide. I will come to this payloads are readable. What do we mean by this? Okay. So first we will discuss some basics of IoT fundamentals. I will not go into much detail. I'm assuming that a lot of things are already discussed for IoT. Then we will discuss what are the issues when we try to monitor the IoT devices, when we try to monitor the traffic that is being generated by one IoT device and the traffic that is being received by another IoT device. What is the problem there? Then what can be the AI techniques? Again, this is a domain which is, I can say this is very hot domain. A lot of research is going on in this. Okay. So there is no hard and fast way of solving this problem. This problem is an open problem. You can see a lot of AI techniques are there. If you think that you can use this AI approach, of course, please feel free to do that. You will see that it is a, since it is a hot domain, I can say that it's a bit easier for you to get papers published in this domain as well. So that is one interesting thing about this particular domain. Real world applications, we will try to discuss, if time allows, we will try to discuss some case studies and practical tools. So when we talk about encryption, so all those, if you are forgetting the idea of computer network, so let me briefly discuss that. I am right now taking the example of TCP/IP suite. So in that we have 5 layers. We can say first one is physical layer. We can say then data link layer or link layer, then network layer, transport layer, and then the application layer. So whatever we are discussing today, that is part of the application layer. We are not going to focus on these things because they will not be affected. They will not be affected whether we are talking about encrypted traffic or unencrypted traffic. Whatever we are talking about, they will not be affected. Okay, they will be same. For clear text traffic, they will be same. For encrypted traffic, they will be same. What will be changed is this application layer. Okay, because when we talk about a clear text, so I'm not discussing OSI suite right now. So when we talk about clear text, whatever data is generated by, let's say one application, let's say your web browser itself. Okay, whatever data is generated by your web browser, that will be forwarded to the transport layer. Simply straightforward, no encryption, nothing. But when we talk about the data is to be encrypted, this data, web browser data, will be encrypted first. We have in OSI model presentation session layer, but I'm skipping that. And then this will be forwarded to the transport layer. So please understand this. This is one extra step that we need when we talk about encryption. So if you take one example, if I'm trying to say, send, let's say, hi, how are you? I'm trying to send this information to someone over internet. This is the actual payload. This is also known as payload, or you can call this as a string that is to be transmitted over the network from a computer A to computer B. Okay. So let's draw them here. If we have this computer A and computer B, and we try to send this string, hi, how are you, from A to B. Okay. Now in clear text, this will be forwarded straight away. But when we talk about encryption, this will be encrypted to XT4P2Q, something like this. And when it is in clear text, on top of this, we have transport layer header attached. On top of this, we have network layer header attached. On top of this, we have data link layer header attached, and then physical layer. Okay, like this. And when we talk about this encrypted traffic, what will happen? Again, the same thing. On top of this, we have TH. On top of this, we have network header. On top of this, we have data link layer. On top of this, we have physical layer. Now see the difference. When someone captures this packet, they will see this content. So they will not understand anything. But in this case, when someone captures this packet, they can see the string. So what is this string? This is the application payload. So that's why we are focusing only on the application layer header. Application layer data, also known as application payload. In this case, that is clear text, so anyone can read this. In this case, it is encrypted, so others can read this, but the problem is they cannot make any sense out of this, right? Because that is there is no meaning to this, right? So what is IoT? Now we have discussed some very basic things about encryption. How does this encryption happen in the network? Then IoT, we have first, nowadays we have consumer IoT devices, smart bulbs, thermostats, wearable. Of course, in India, I'm not sure if this is a common device. Still, it is not common device, right? We have wearables, right? Wearable means, I mean, your smart watch and all. Then on top of that, other than your home automation systems, we have industrial IoT as well, SCADA for your for this power smart grids, manufacturing sensors, right? Healthcare IoTs are there, monitors, fitness devices are there. So all these are part of the IoT environment. Network of interconnected devices with sensing, computing, and communication abilities. Please remember these three things: sense, compute, communicate. These three things. And based on these, we have three layers. First is application layer, and by the way, in this presentation, we are focusing on this one. Okay. Then is the network layer. So basically, when we talk about this application layer here, we are talking about this particular computing, this complete part, complete three part. Okay. Then when we talk about network layer here, communication is going on. And then when we talk about perception layer here, basically we have sensing going on. Okay. The physical devices, sensors, actuators, they interact with the physical environment. So if you talk about, let's say, moisture sensor, right? It can be moisture sensor. It can be a smoke sensor, smoke detector, something like that. What are all they? If they are connected to a network and they can generate some network traffic, then that means that they are smart sensors. Okay. The network layer, so basically how they are transmitting this data, whatever they captured, let's say they captured the temperature is 30 degrees Celsius. Let's say they captured this data, how to forward this to a dashboard running on the application layer. Dashboard basically means you can say a web interface. You can say a web interface that we can see on our, let's say, web browser. Okay. We have a simple web browser, web GUI, web interface on which we can, yes.
So sorry to interrupt. The participants facing difficulty to see the marker color in red. So ask them to.
Okay, so you have difficulty in. Okay, let me
they
change.
Can't able to read in red color, so they request to change the marker color to some.
This blue is fine. Could you please confirm?
Yeah, blue or yellow or green is fine. Yeah, blue is fine. We can go with blue.
Blue is fine. Okay.
Yes.
So I have written both. I think yellow is better.
Yellow is better.
Yes.
Yeah,
perfect. Yeah. Perfect. So okay, let me use the yellow then. Okay, fine.
And also,
thanks for the update.
I will post the comments whichever the audience are raising. So if possible, you can try to address meantime.
Okay, just trying to change. Okay. Okay, fine. So till now we have received the comment for marker color, right? Okay, perfect. Okay. So now we were talking about at application layer, we have web interface where we can see the content that is generated by the sensor. So in this case, the content is basically the temperature, right? Now, how is this happening? Sensors are somewhere else. They are somewhere in real field. Let's say maybe on a road, okay, or outside a building. We can say that is a better example, I think. Outside the building, right? But of course, you are not seeing all these things outside the building, right? You are sitting in your office. You have a computer. You have monitor where you have the web interface, right? So that means that the data from this sensor outside the building is being forwarded to the dashboard, which is running on your system, right? Now, how this data is forwarded? That is the responsibility of this network layer. It transfers data. It can be either your Wi-Fi. So let's say the sensors are directly connected to Wi-Fi, or it can be through Zigbee controllers, then low range this communication system, and or cellular communication. Cellular communication basically means that we have IoT gateways where we can use directly our SIM cards for the data transmission. Okay. So the idea here in this architecture is we need to understand three layers. First layer, we are talking about our computers, okay, where we can see the actual data. Okay. We can capture the data, we can analyze it, we can perform some operations on that, we can pre-process them. All these things are happening at the computer. Then last layer here, basically perception layer, where we have actual sensors, physical devices which generate the data. Here the data is being generated. Now how these two work in tandem with the help of the network layer. So these generate data and they forward the data to the application layer through the network layer. Okay. So this is now overall concept. Now we will focus how the traffic is encrypted at application layer, and then how it is difficult for us to find out the issues at the network layer in case the traffic is encrypted. So till now we have seen the advantage of using encryption. The advantage was that confidentiality was ensured, right? Confidentiality was ensured. Okay, this is the advantage of using the encryption. So what is the problem now? And this is what we will see in this presentation. So this, I hope all of you know that it ensures that privacy is maintained and all those things. So what is the problem now? And that's what we will see. And coming to this communication protocols, when we talk about this network layer, we have different communication protocol depending on the requirement. We can have different ways through which we can communicate. Most popular protocols are, I think I missed one. One is basically AMQP. Okay, I'm forgetting the complete word. I think it's message queue protocol, advanced message queue protocol, if I'm not wrong. Okay, message queue telemetry transport protocol, then CoAP. What? So basically, these two are based on TCP. Okay, transport layer protocol. TCP is used for these two application layer protocols, MQTT and AMQP. But when we talk about CoAP, it uses UDP. Okay. So now the idea is all these protocols, they can have encrypted traffic. Okay. We can have HTTP and HTTPS also that we see in our normal computers. But the problem is HTTP and HTTPS, they are not lightweight. They are quite heavy protocol. Okay. They were designed for our normal computers. Okay. When these protocols were developed, HTTP now, I think it was 1990s, if I'm not wrong, the 1.0 version. Okay. Now we are using HTTP 3, but I'm talking about HTTP 1.0. At that time in 1990s, of course, we didn't have anything related to IoT, right? At that time we have, okay, so in between, I got some questions. I will come to these questions just a minute. Let me finish this part. Okay, so in 1990s, there is no concept of IoT. At that time, we have only concept of we have the concept of only normal computers, and at that time, HTTP worked very well. Even today, also HTTP is working very well. But there is a huge limitation to that. It cannot work on very resource constrained devices like our IoT devices. So for that purpose, we have things like MQTT, we have things like CoAP, and all those who are interested, you can read about AMQP also. Okay, these three protocols. These are the major protocols basically which are being used. Okay, so these are the some communication protocols. Now let me see the questions just a minute. Which encryption model is used for tunnel? So as I said, depending on what is your requirement, so we can use ECC also for the encryption. And by the way, this is not a tunnel like VPN, right? Here we don't create the VPN. Here we simply create the encrypted content and we forward that to the receiver. Okay, there is no actual tunnel that is being created between the sender and the receiver. Then please explain future scope challenges. Okay, I will come to that. How to identify network traffic attacks. So again, this network traffic attack, till now we have discussed MITM. If you want to detect MITM, we have to work on things like ARP poisoning detection. Okay, that is altogether different topic, by the way. Since you asked, I mentioning that. All those who are interested, you can read about this ARP poisoning detection. Okay, but that has nothing to do with IoT. Okay, can we use a network security algorithm for this encrypted data? So yes, we are using network security algorithms, right? So all these cryptographic algorithms, they are used for encryption only, right? We are using them for the encryption, and at the same time, at the receiver side, we are using them for the decryption as well. Okay, I hope that answers the question. If I couldn't understand, you can rephrase the question. Which algorithms can apply for this medical IoT encrypted data set? Now we have, so all those who are interested in this, since my domain is not medical IoT healthcare devices, but all those who are interested, I will tell you what you can do. You can refer to NIST. Please go through this. This is one important topic, by the way. NIST lightweight cryptographic algorithms. By the way, all the researchers who are working in healthcare domain, they are using these cryptographic algorithms frequently. Okay, they are working a lot on these cryptographic algorithms. So if you go through this, simply Google this. So NIST, what it does, it conducts some contest where they select lightweight best cryptographic algorithm. So like Crystal Kyber is one. I can recall one right now. Crystal Kyber is one. Then like this, we have multiple cryptographic algorithms. I think MacAlice or something. I'm not sure if this is the exact name. But like this, we have cryptographic algorithms which can be used for light IoT devices, the resource constrained IoT devices. So when we talk about medical IoT devices, since they are resource constrained devices, we can ensure that we can use these cryptographic algorithm for the encryption. Of course, make sure you don't use RSA for them. You cannot use them, right? So just go through this, simply search on Google NIST lightweight cryptographic algorithm, the top 10 cryptographic candidates. Okay. you will see a list of algorithms that you can use for encryption. And by the way, these all are open source. Okay, these are not proprietary cryptographic algorithms. These all are open source. You will get the code for this. You will get complete guide on how to implement this cryptographic algorithm on your devices, how to execute them. You will get complete detail of all these. Okay, they are not proprietary. I mean, they are not from any particular organization. Okay, they are completely free. Okay. Okay, coming to the growth of IoT, again, this is something not directly related to the point that we are discussing right now, but just the motivation why you should work on this IoT security, on IoT network security. The reason is right now we have, again, this is I think 2 to 3 year old data. This was for financial year 23 to 24. Okay, 15 billion plus connected devices, and here we have our smartphones, smart televisions, smart CCTV cameras, smart sensors, smart watches, and all those things. All of them are connected to internet today. Okay, 25 billion, it will reach to 25 billion by 2030. You can see the growth. Almost now 10 billions will be added by within next 5-6 years, right? Attack surface. Now, when we talk about this number of devices, if let's say you find a vulnerability V in one device, let's say a Samsung mobile phone, not let's forget the mobile phone. Let's say maybe one CCTV camera. Let's say you find a vulnerability in CCTV camera whose name is C1 from some XYZ vendor. Okay, I'm not specifying anything. Please don't understand that. I am simply mentioning a generic this CCTV camera called as C1, which is having a vulnerability V. Okay. Now, what will happen if let's say this CCTV camera, this vendor is very popular. Okay, this company is very famous in all different countries, and a lot of people are using this CCTV camera. Then of course the attack surface will increase because this vulnerability V will exist in all those devices. So if let's say 10 million CCTV cameras are being used, 10 million C1 cameras are being used in the world, that means that all of them are vulnerable to this vulnerability V. But if we take, let's say, one camera C2, which is not that famous, and only maybe within India it is being used, and let's say 5 lakh people are using in 5 lakh households, it is being used. In that case, what will happen? The attack surface is automatically gone down. This is known as attack surface. More devices means increased risk. Okay, because if you find a vulnerability, that vulnerability will be applicable to more number of devices if the device is popular, right? Now, okay, why is encryption used? First, confidentiality. Okay, I hope this we have already discussed, so I'm not going to discuss this again. Then there is something integrity. When we talk about the same topology, let's say we have two users A and B, and in between here we have C. Earlier we were talking about this topology, this communication model. Okay, A is trying to communicate to B, B is trying to communicate to A, but in between the C was not there. So C was trying to capture some data like this. So here confidentiality is compromised. Okay, means that privacy is compromised. But if we change this, if somehow attacker changes this topology, this communication model to like this, now what is the problem? Can you tell whether integrity is compromised here? Yes or no? Anyone? So if you see, integrity is also compromised. Why? Because in this case, integrity basically means that the data can be modified. Whatever A is trying to send to B, C can modify the data in between. Whatever B is trying to send to A, it can also be modified by C. In fact, availability is also compromised. So if you know, cybersecurity is relying on these three things: confidentiality, integrity, and availability. We have discussed confidentiality, we have discussed integrity can be compromised in this case. In the same way, availability can also be compromised. How availability will be compromised? Because when C is in between A and B, whatever A is sending to B, that is going through C. So what C will do? C will simply drop that. Drop it. Don't forward to B. Whatever B is sending to A, simply drop that. Don't forward it to A. The problem here is now the message is dropped. This leads to denial of service. Okay. Very famous attack known as DOS attack. So in this case, availability is also compromised. So all these three things are compromised. Okay. Since we are talking about encryption, so we do not discuss in general availability. So that's why I have not mentioned it. Authenticity. how to identify who is the sender of this particular, how to identify who is the sender of this particular message. So there is something known as digital signature. Okay, that is again one concept of cryptography, encryption. Okay, so for that also we use encryption. For compliance required by GDPR, again all the basically your data protection laws which are there, which exist in different countries, right? So this is for America. Okay, I'm forgetting the full name for this, but this is for America and this is for complete European countries. Okay. So what happens in this case? Basically, what they do, they ensure that the data is not compromised with the help of encryption. Types of encryption. Now, one of you asked this question. We can have TLS SSL based encryption where we encrypt the data, transport whatever is after transport layer, that will be encrypted. Okay. When we see HTTPS, please ignore this SSL. Nowadays, we are not using that. That is obsolete now. When we talk about HTTPS, in that case, we are talking about HTTP plus TLS. Okay, please remember this. This TLS is nothing but this, whatever we are discussing right now. Okay, transport layer security. Okay. Then we have another version of TLS, the datagram transport layer security. This works for UDP protocols, not for TCP. Then we have symmetric cryptographic algorithm, AES, right? That is of course lightweight as compared to your RSA, right? Then we have elliptic curve cryptography. These are a bit lightweight as compared to these RSA and other cryptographic algorithms. So they can be used for IoT devices. But again, these are very old cryptographic algorithms. So we have much better algorithms than these nowadays. As I mentioned, if you search for NIST lightweight cryptographic algorithms competition or the contest, you will see the winner, second runner up, first runner up. You can find out the name of those cryptographic algorithms. So if someone in the participant, if you are working on, let's say, the communication part for IoT devices, and you assume that you need encryption, what you can do, you can refer to this content. Okay, you can refer to the different cryptographic algorithms, find one, just see the name, that's it. Name, just check the name, that's it, and simply search that name on Google. You will get the GitHub repository for that. You will get the code for that, and then you implement it on the device. Okay. Now let's see the limitation. That's very important. Again, this is the challenge that we are facing as a cybersecurity researcher. We are facing this. Okay. Limitations of encryption. First, when we talk about hi, how are you? Everything is understood. If you take the same example again, now we don't have C, we have, let's say, a legitimate, let's call this as firewall. It is not a firewall, but to make it simpler, I am calling this as a firewall, let's say. Okay. Whatever data is being communicated, that will be captured by firewall. Firewall will analyze what is going on between A and B. It will simply read the content. Okay. Whatever content is there, based on that, firewall can take action. But in case you simply encrypt this X to PA 5 TQ Z, something like this. Now the problem will be this legitimate firewall, poor firewall, it will not be able to understand what is going on between A and B. Though this firewall was deployed for better purpose, right? It was deployed to ensure that it can check what is the content that is being communicated between A and B, right? Because if you can take your university network, right? If you do that, what will happen? It will be something like this, Okay, this is your local area network. Here is your computer A. It is trying to communicate to B. Let's say the communication is happening like this. Okay. If it is encrypted, if this content is encrypted X2 A5 P T Z, something like this, and we are assuming end-to-end privacy from here to here, no decryption in between. Please remember this assumption, no decryption in between. In that case, this firewall will not be able to understand the actual content that is being discussed between A and B. So if it is having one string that should not be searched over internet, the legitimate firewall cannot do that, right? So this is the biggest challenge that we face because of the opaque payload. The payloads are not transparent, right? Security tools can't see inside packets, of course. Then we have seen now the advantage is there, but at the same time, this advantage comes with a huge cost. That is the security tools cannot check the content in the packet. IDS limitation. So basically the firewall that I mentioned, it is nothing but IDS. There is a huge difference between IDS and firewall, but I did not want to create confusion by discussing IDS and firewall separately. So just assume that we are talking about IDS right now, intrusion detection system, which cannot understand anything if the data is encrypted, right? So it cannot scan encrypted content. Port confusion. Now chances are that we have something known as TCP and UDP port. Okay, we have all these things, TCP and UDP port. Okay, we got a few questions again. Let me finish this and then I will take the questions. Okay. So here what happens, the very common services like service HTTPS, it works on port 443. We have service HTTP, it works on port 80 and so on. So like this, we have services. But again, this is not necessary. You might have seen some websites in your local area network that is hosted on port 8080 also, right? That is not a, generic port, right? It is randomly defined by the network administrator. So we can do that, right? So of course, with the help, because of this, we cannot identify which service we are capturing the packets from. Okay, it is very difficult. So one thing that we can rely on is the content of the packet. But since now we are talking about the encrypted content, we cannot read the content also. So that is the limitation of the encryption. Let's see the questions. Need how to avoid uninterrupted traffic. How to avoid uninterrupted traffic. So I'm not able to understand your question, Chiranjeevi. I'm not sure if, what are you trying to ask? Could you please rephrase the question? Meanwhile, I will check the other questions. So merely asking any technique for detecting those attacks. So yes, we have a lot of techniques. We have IDSs based on your support vector machines. We have IDSs based on federated learning, right? They can analyze the different features of your packet. We will discuss the feature in a minute, just a minute, okay? And based on that, we can take actions. Which layer is most likely to be attacked and why? Now, the problem here is, so surprisingly, there is no single layer in the OSI model or the TCP IP model that is most likely to be attacked. Most of the attacks that we see nowadays are based on application layer because it is easier for us to launch the application layer today. Network layer and transport, a lot of attacks have already been done in the past, because of which they are very well robust now. Okay, it is very difficult to find attacks against network layer and transport layer. So TCP, again, a lot of attacks were found in the past, in 1990s, in early 2000. Okay, so now that is completely patched. You cannot launch those attacks. IP, there were a lot of issues earlier, but now it is completely patched. So it is very difficult for you to launch attack on these core protocols. But yes, you can launch attacks on other application layer protocols. So in a nutshell, if I say, if I want to answer this question, I can say that you can refer to the application layer because that is the easiest target for the attackers nowadays. So Radha is asking, in CNS, we are using so many algorithms like RSA, CC, Diffie-Hellman. Okay. So based on our requirement, when these algorithms are used in encryption process. Yes, they are being used for that. So Diffie-Hellman technically we not only used for encryption and decryption, but they are used for places where we need to exchange a shared key between the client and the server, or the sender and the receiver, because we cannot rely on the asymmetric cryptography. Asymmetric cryptography like RSA, it is, as I mentioned, it is very huge. I mean, it needs a lot of resource, right? It needs a lot of computational power. So you cannot rely on that. Then can you rely on the symmetric cryptography like DES, AES? Yes, you can rely, but the problem is the key distribution is a difficult thing because encryption and decryption is happening with the help of the same key. So how to distribute this particular key? And that is where Diffie-Hellman key exchange come into picture. Okay. So, I mean, these are the limitations of the encryption, because of which we need to shift our focus from content to behavior. And as soon as we shift our focus from content to behavior, AI immediately come into picture. Why? Because when we were able to see the content, there is no need to check, implement, no need to, deploy AI algorithms, right? AI algorithms, of course, they need a lot of extra burden. They come with their own extra overhead, right? You need to execute them on computer. Again, a lot of processing power is needed for that. So if there is no need to implement AI, why to implement AI, right? So when we have only content, based on content, you can identify whether this is attack or this is normal, then there is no need to deploy AI algorithms. You simply see the content. If content is XYZ, declare this as attack. If content is ABC, declare this as normal. That's straightforward. No need to deploy AI algorithms. But as soon as the content is now encrypted, so we lose our access to the content. So we have to focus on something known as behavior. How the traffic behaves, how many packets are being transmitted. Please understand the difference. Content and behavior. Content is, hi, how are you? Behavior is, what is the size of this packet? When this packet, the first packet was sent, when the last packet was sent, what is the inter packet time? I mean, when the first packet was sent, when the second packet was sent, what is the difference, time difference between these two? Okay. How many packets were sent? How many bytes were sent? How many bytes were received? All these are what? These all are features in behavior. And these are the features which are used by the AI algorithms to detect the anomalies. So one of you asked what I can mention here. First, size of the packet, because if you encrypt the packet, the size will not be encrypted, right? Size will not be encrypted. You can still find out the size of the packet. Yes or no? Then what else? Inter packet arrival time. When, sorry, inter packet arrival time, when the first packet is received, when the second packet is received, what is the time difference between these two, and so on. How many packets, we can say number of packets. Like this, we can have multiple features. A lot of features are possible. Okay, let me write it here. Then we can have, let's say, what else did we discuss? Okay, number of bytes transmitted. Now, even if the data is encrypted, we still can access all these things. Okay, number of bytes received, all these things. So I'm giving this 5 example. Like this, we can have multiple features. It is not a comprehensive list where we can have only 5 features, but we can have multiple features, right? These features are given as input to the machine learning algorithms, and then the machine learning algorithms, they try to find out the anomaly. Now, how accurate is this? Of course, there is a huge challenge to get a good accuracy. It is very difficult to get good accuracy. Usually, we should not say that, but we see a lot of papers that are being published in this domain. We see they are getting good accuracy, but the problem is either the data set is very small, or that is not in real time. If you try to deploy that in real time, you will see the accuracy immediately goes down. And if you try to increase the accuracy, if you try to increase the performance, you will see that it will not be able to detect the attack in real time. It will take a huge amount of time to detect the attack, and by that time everything will be gone, right? This is the biggest challenge in network security. You need to detect the attack in real time. You cannot say that I will detect this attack after every half hour. You cannot do that. Within half hour, a lot of things can be done, right? Attacker can do a lot of things. So that is the biggest challenge. You need to find the trade-off between the accuracy, and you need to find the trade-off between accuracy, and second thing is the real-time detection. Okay. Okay, so again, we got a few questions. How can generative AI model be applied to analyze or simulate encrypted traffic pattern? Now, again, here, this is no different than your normal AI models. So what I can say is, in fact, I have not used Gen AI models till now. But what we can do is, you can simply use the APIs that are there. So all these Gen AI models, they have their APIs available, right? You can use them, simply use them. They are like black box, but what you can do, you can use the API. You can give them the traffic, network traffic part. Of course, you need to process the network traffic first for all these 5 features, let's say, that we have discussed here. Okay, these 5 features. Tell to the AI model that, okay, these are the 5 features. Based on this, check whether this flow that we are getting is normal or anomalous. Then that AI model can simply respond that. Okay. But the thing is, yes, you have to parse that before. You have to pre-process the traffic first. Okay. And then, if I'm not wrong, all these popular Gen AI models, they have their own APIs that you can use in your code. Okay, you can do that. But I'm not sure which one will give better result, because I have not used till now. Since, as I mentioned, this is a very new domain where a lot of research is already being done, and I'm not sure if anyone has used till now Gen AI model to detect anomalies in encrypted traffic. And I think, as far as I know, to the best of my knowledge, there is no paper which is discussing what is the performance of generative AI model on encrypted IoT traffic, by the way. Okay. Then Preeti is asking, sir, can you tell what is the basic difference between AES and DES in encryption? So again, in a nutshell, if I say DES is very old algorithm, we have, in that case, we have only 64-bit keys. Since if the key size is less, the problem is in that case, it will be very easy for us to break the algorithm, break the encryption. So if you give one string to someone, to the attacker can find the corresponding clear text. So that is the problem. That was the problem with DES. Since anyone can break DES, I mean the nowadays which the computers that we use, i5, i7 processors, they can break AES. They can break DES very easily. To avoid that, we shifted to AES, and AES is basically the advanced encryption standard. Okay, so this AES is now much more secure as compared to DES, and that's why we are using AES nowadays. Okay, Sulma is asking, has encryption have any use in GAN network or in GenAI? GenAI I have already mentioned. I'm not sure about again GAN network. As far as I know, graph neural network is one domain where people have already uh, done a lot of research on that, how to find out anomalies in clear text traffic using graph neural network, but I'm not sure about this encrypted content. So I cannot answer that part. But yes, GenAI, as I mentioned, there is no research has been done till now on that part. How AES and ECC is different. Again, as I mentioned, ECC is basically based on elliptic curve. It has a lot of, then again, we have to go off topic from this discussion. But please remember that AES is symmetric cryptography algorithm, while ECC is elliptic curve. Okay, so both are different ways of encrypting the content. But the similarity is both are both are lightweight. They are not heavy as compared to if we compare it to RSA. Then Disha is asking, is anomaly detection is useful in this detection? Yes, of course. So whatever we are discussing right now, that is anomaly detection only, because as I mentioned, now we do not have access to the content. Why we do not have access to the content? Because the problem is the content is encrypted now, right? So we cannot have that. We have to focus on the behavior. And when we talk about behavior, we have to talk about anomaly detection. So also known as behavioral anomaly detection. Vinayak is asking how to protect application layer from attacks. Again, as I mentioned, you can work on encryption. Encryption prevent a lot of attacks, but the problem is, we are discussing, this encryption comes with a lot of issues. Okay, and that's what we are discussing. There are so it has both the things, heads and tail both. Head, this is very much efficient. If you do use encryption, you can mitigate a lot of attacks. But at the same time, tail, the problem is the legitimate security tools, they cannot read the content of the packet. Priya is asking encryption, which type of security key use? So as I mentioned, depending on the cryptographic algorithm, we can have different length of the key, 64-bit, 128-bit. In fact, RSA nowadays 2048-bit key is very common. But of course, if you increase the key size, the problem is the overall time needed to encrypt and decrypt will also increase. So that's why we can say that RSA we cannot use on any resource constrained IoT devices. What type of encryption standard be implemented for analyzing? What type of encryption standard be implemented for analyzing? I'm not sure what is the question. Priya, could you please rephrase this question? And meanwhile, you write the rephrase question. And meanwhile, I will discuss the other topic. Okay, and then I will get back to your question again. Okay, why encrypted traffic is hard to analyze? First, DPI. This DPI is known as deep packet inspection. Again, a very interesting domain in the network security and machine learning, deep packet inspection. When you talk about deep packet inspection, that means that you are talking about the content of the packet. But as soon as you talk about the content, if it is encrypted, this DPI is completely gone. Big cross. Okay. So these people have worked on this since last 15 to 20 years. A lot of work is published in this, very good papers, research papers, seminal research papers are there. But now they are completely gone. You cannot use them in the real world. Why? Because now we are talking about encryption, right? Labeling issues, cannot tag encrypted flows easily. Since we don't know the actual meaning of the content, we cannot label them, whether it is normal or attack, varied standards. Encryption implementation differ widely. Quite a few of you also asked difference between AES, ECC, DES, right? Then Crystal Kyber, the one that I mentioned. Okay. MAC Alice. The problem with these is basically these are different types of cryptographic algorithm, and if you change the cryptographic algorithm, of course implementation will also change. So that is the biggest challenge that we see in encrypted traffic. If we talk about IoT specific challenge, now we are talking about the intersection of IoT and the machine learning, IoT network traffic and machine learning. Okay. Device behavior, it varies under normal load. Let's say the resource consumption is quite normal right now. Okay, you have the IoT sensor is having a good amount of RAM available, good amount of processing power available. It will work differently. And when the battery will go down or the processing power is not available that much, then it will behave differently. That is the problem. Protocols, they are not standard. I mean, it can be proprietary also. Any vendor, let's say new vendor comes into the market, they develop their own type of sensor that will use its own protocol for communication. So since that is not a standard, so we cannot create a detection or mitigation algorithm that will work for all the cases. That will not work, right? Because different sensor will behave differently. Monitoring, no agent based options are there, because we will discuss this in predicted learning. Firmware updates change baseline. As soon as you change the firmware, you will see that whatever data you have collected for training right now, that will not work for the future now for testing, because now the traffic behavior is changed. As soon as you update it, update the firmware, update the hardware, then immediately the behavior will change, or the traffic type that is being generated will be changed. Now the consequences of these blind spots because of the encryption, since encryption is there, so because of that we have a lot of blind spots in network. Hidden threat actors operate under encryption. So let's say a malware is there, right? Malwares have their own signatures, and if the signature itself is encrypted in the packet, how will a firewall or how will an IDS detect that? It will not be able to do that, right? And that is the biggest problem that is faced in this case. Okay. Lateral movement. I believe a few of you have, most of you have heard about these worms. They replicate themselves. Let's say one computer in the network is corrupted with a worm. What will happen? It will be replicated to all the other computers within the network. Okay, and because of that, what will happen? Just a minute. Okay, because of that, what will happen? In that case, all these systems within the network will be simply affected due to this worm. Okay. Weak detection. If we cannot read the content, of course, the detection will be very weak. Now comes the question, why use AI? Because till now we have discussed that content we cannot access, we can no longer access now because of encryption. If you don't use encryption, then the complete altogether different types of attack will be there, right? So to avoid that, we use encryption. But now again, the same problem, if we use encryption, a lot of other types of attack will come. How to detect those attacks now? So there AI comes into picture. We have pattern recognition. So what we will do, we will capture some traffic, train that basically on 5 features that I mentioned. Okay, we will train machine learning models based on those 5 features. Let's say, again, this can be more than that, but I have taken the example of 5. Okay. And then based on that, we can test the incoming traffic during the testing phase. So this is the easiest way, pattern recognition based on these features. Statistical analysis, here there is no need to use the machine learning algorithms. We can use techniques like, please, if you are interested, you can note it down. All these things are, very hot domain, and a lot of people are have started working on this. Okay. Hellinger distance, again, this is very old. This is very old way of detecting anomalies, statistical anomalies. Okay. You might have heard about Euclidean distance. All these are what? They are statistical abnormality detection techniques. Okay. Then part of this is anomaly detection. Okay. Identify outlier and malicious behaviors using either pattern recognition or statistical analysis. Then how this AI works for network security? We have, of course, like other cases, we have pipeline. First, collect data. This can be from within your network. Okay. Let's say you create a dedicated computer. You have a dedicated computer in your network that can capture the complete traffic. So this will capture the complete traffic. Now, how to capture the complete traffic? We have a tool. I will mention the name. You can read this out. What is this? TCP dump. Okay. This is one tool that can be used to capture the network traffic. It can be clear text network traffic. It can be encrypted network traffic. You can capture this. Once you capture this, what you need to do? You need to perform the feature engineering. Find out what features you need to detect anomalies. Okay. So I hope there are, you guys know ways how to find out the best features out of one data set, right? all those things. We can perform feature engineering to find out which are the best features. Now, for this, we have already a few papers which mention what are the best features, okay, that we can capture to detect anomalies with better performance, with better accuracy. Once you work on the feature, you train the model, okay, it can be either supervised machine learning algorithm or unsupervised learning. Unsupervised is much more popular. I would say, again, you can argue on that, but I think unsupervised learning is considered as more popular in machine learning, in network security. The reason is they have this tendency to take zero-day attack also. So what will happen in this case? You train them with the normal traffic. That's it, just normal traffic. Whatever they will receive in the testing phase, if that is abnormal from whatever they have been trained with in the training phase, they will immediately detect that as attack, right? So anything other than normal, they will consider that as attack. So it's a bit easier because it is very difficult to find data sets in network security, right? So supervised algorithm, it is very difficult to do the labeling to find out which is what attack or and something like that, okay? Inference, then you try to deploy that. Deploy basically means that now you have to focus on two things: real-time detection plus performance. Okay, it is not like you try to detect the attack immediately within 30 seconds, but you will get the performance of, let's say, 30% accuracy only. Okay, I'm just giving an example. And then it is not like you can say it will take 30 minutes and it will give you 99% accuracy. You cannot rely on that as well, right? So you have to make sure that there is a trade-off between these two things, these two parameters: real-time detection and the performance metrics. What can be analyzed? Packet size. We can analyze this. We can identify the time when we receive different types of packet. What are the protocols? Again, all these fields are present in the packet itself. So we can analyze this. This is not present in the content. Okay, so we can have access to all these things. Connection sequence. So something known as three-way handshake in computer network. We have something known as three-way handshake. Then after that, packets transmitted. In this, we can have multiple types of packets: A, B, C, D, and so on. And then after that, the FINAC. Basically, the connection is terminated. So we have something like three-way handshake, then A, then B, then C, then D, then FINAC. So you can say this is an event sequence that is generated now. Okay. If your event sequence is disturbed in the testing phase, you can say that there is something wrong in the flow, right? So this is one way of finding out the anomaly. Behavioral fingerprint, again, all these, when you establish the connection, we have fingerprints set up in log files, right? In log files, we can see a lot of different logs are appended, different events are appended to that. We can rely on that also. We can find out anomalies in them as well. Now, what AI models can be used? One of you asked. So again, this is not a comprehensive list. It's up to you which one you want to use, depending on what type of anomaly you are trying to detect. One of this can give you good result. One of them will not give you the good result. Okay, so you can try them. SVM. Quite a few work has been published on support vector machines. Decision trees. Again, it is very easy to detect using decision trees. But now, when we talk about encrypted traffic, it is not easy to get good accuracy with the help of decision trees. Okay, random forest, clustering algorithms, again, most common one, most popular one for network security for encrypted traffic, autoencoders, isolation forest. Then for deep learning, LSTMs, CNNs, reinforcement learning, adaptive responses. So all those who are working in the machine learning domain, this is for you. You can go through this, try to find out one data set. Okay, try to implement these algorithms and see how much result you are getting, how much accuracy you are getting. The idea is basically the main motivation, the main novelty of your work will rely on what type of features you are extracting from the traffic. Okay. Then we have something known as federated and edge learning. Again, this is basically this came into picture for network security only. You'd be surprised to know that, because sometimes we don't want to reveal our data to some centralized location, right? We simply don't want that. So what usually happens, the sensors, they can have their own data, and based on that they can decide whether it is normal or anomaly. So that's why we have this federated learning. Again, very new domain. Very few research has been done on this for encrypted IoT traffic. Edge learning, again this is part of basically federated learning, where we try to take decision on the edge devices itself. We don't want to forward the data to the a central device first. The all data will be accumulated there, and then based on the complete data, some decision will be taken. So in that case, privacy will be compromised. So to avoid that, we have the federated learning concept. If we talk about, so I think we don't have time for this. Okay, let's try to discuss this smart home case history. Infected smart TV. So here, let's say we have one smart TV in our home, right? All of us have smart TV nowadays, right? Let's say, let's assume that it is compromised through a malware, okay? Because these television, these smart devices, they are not that secure. Unlike your laptops and mobile phones, laptops, mobile phones, they are very much secure because they are designed to work accordingly, right? Based on that. But television is designed to just to show you some audio, video, right? That is the purpose was different. So when the vendors developed the smart TVs, they don't rely much on the security part. They see just the performance part. The picture quality should be good, the audio quality should be good. There should be a lot of functionalities, right? But they don't focus. They don't put much emphasis on the security component in these devices, smart refrigerators, smart CCTV cameras. So because of that, there are a lot of vulnerabilities that exist in these devices, and because of those vulnerabilities, anyone can exploit it to affect them through a malware. Okay, once it is compromised with a malware, in that case, what will happen? You will see sometimes, let's say, if you find out that in midnight, let's say, a lot of data is being exported somewhere. So a lot of data is uploaded. Okay, a lot of data is being uploaded at let's say 11 o'clock, 11 p.m. That means that there is something wrong through the in the TV, right? Why is it happening that a lot of data is being uploaded from your TV to somewhere else, right? So immediately you will find out that there is something fishy going on. Pattern detection, all these things can be analyzed with the help of AI, and this is what we call this as behavior. Okay, behavioral analysis. AI identifies abnormal volume, timing, no decryption needed, because now we are talking about the statistics. We are talking about the statistics. We are not talking about the content. Please remember, understand this. We are not talking about the content. We are talking about the stats now. Okay. If we talk about healthcare, IoT case history, we have ECG monitors, right? What is their responsibility? Basically, they ensure that all the stats or the vital stats of the patient is fine, right? The challenge is maintain patient privacy while detecting anomalies. So here we can use federated learning. Again, this is a new domain. I mean, quite a few papers have been published in this. But again, if we change the data set, chances are that the algorithms will not give you good result. So what will be your contribution if you work in this domain is you first have to create the data set. So if you, let's say, visit a hospital or you are working in collaboration with a hospital, try to get the data set, okay, and then try to work on that. Then try to deploy different cryptographic algorithms to find out whether they will work. I mean, they can give better accuracy or not. Okay. So since we want to ensure that privacy is not compromised, what we can do, we can deploy federated learning. Okay. So that the anomaly that can be detected at ECG monitors itself. There is no need to forward. So let's say multiple ECG monitors are there. All of them will be forwarding the data to this central database. This is a central database. This is not needed. This should not happen. In that case, the privacy will be compromised of all these patients here, 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 and here. Instead of that, what can be done? Action can be taken. I mean, the detection can happen here also, here also, here also, here also. And then based on that, some cumulative decision can be taken. Okay. Then we have industrial IoT case history environment. So factory with a lot of programmable logic controls and human machine interfaces. Okay. Here, there is something known as SCADA, again, related to smart grid. If you see, you will see a lot of issues that is happening. And when we talk about, current this world affair where we see that, lot of, we don't have good relationships with a few countries where our smart grids can be compromised. A lot of issues are there in our smart grids in India, and people in our adversarial countries, the countries which are adversary to us, they are trying to launch attack on these smart grids, and that is the biggest challenge that Indian government is facing. The smart grid infrastructure, a lot of issues are there, and they are trying to mitigate them. They are trying to detect the vulnerabilities to find out different types of attacks, and for that we have this case history of on industrial IoT. Okay. Attack, so environment factory with PLCs and HMIs, attack abnormal control messages sent to machinery. All models, AI models detects deviation from learned state machine transition. So machine transition is nothing but your event sequence analysis only. So let's say machine is at state X in the initial phase. It receives a packet A, it moves to state Y. Then after that, it receives a packet type B. Then it moves to Z. If it receives a packet type C, then again it moves to state Y. Okay, so this is basically state machine transition that you can also create with the help of this event sequence analysis. Okay, now on top of this, you can adopt, you can implement, you can deploy different types of machine learning algorithms. TCP versus NDN, again, this is something that is out of your discussion. I mean, I will try to skip this because this is, again, there are a lot of issues in TCP, and nowadays people have started moving to NDN. So all those who are interested, you can just refer to this. You will find out the issues in TCP IP, which is being used over internet since last 50 years. Now, I think, yes, it's been 50 years since we are using TCP IP, the complete internet, the current internet architecture. Since there are a lot of issues, to avoid this, we have a new internet architecture called as named data network. Okay, named data network. So all these IoT devices, people are trying to ensure that they can use NDN for communication instead of TCP/IP. This is groundbreaking research, but still a lot of challenges researchers are facing. But they are working on the simulators. They are not working on the real hardware till now, but they have started working on the simulators. Okay. So all those who are interested, you can read about simulators like NDN Sim. Then you can read about Icarus. Okay, so and then we have one more Python-based NDN, that is Mini NDN. Okay, so these are some of the simulators where the people are trying to work on finding out how NDN can perform better than TCP/IP in different use cases. Okay. We have traffic analysis tools. So one, we have already discussed TCP dump. Like this, we have multiple other tools like Wireshark. Please go through them. You will see that they are very interesting. You will see how packets are being transmitted from your computer to other computers. Okay. Wireshark is a bit easier because it is a GUI, but the problem is it cannot capture a lot of packets. But TCP dump, this is a command line based tool. So it can capture huge sizes also, 10 GB, 15 GB, depending on how much space is there in your hard disk. It can capture large PK files also, but this one cannot capture large PK files. It will consume your whole RAM otherwise. Okay. We have public data sets. Now, again, this is not a comprehensive list. Now we have a lot of other data sets also. In custom data sets, we have quite a few recently published data sets in 24 and 25 from the CI/CD itself. Okay. For ransomware, for encrypted malware, traffic analysis, all those things. AI development framework, again, I think a lot of you have already worked on this. Deep learning, you might have worked on TensorFlow, PyTorch, okay, for complex pattern recognition. So I'm not discussing these part. I guess given one problem statement in network security, that is the encrypted network, you can deploy all these things. What are the research challenges that we face as a researcher in this domain? First is label scarcity. There is the data set is not readily available. Okay, whatever data sets we have, there are a lot of issues with them. It is not like if we have 10 data sets, all of them are good to go. Okay, there are a lot of issues with them. Okay, a lot of challenges are there. Real time constant, one very important. This is the most important, by the way, the one that we face. If you try to make sure that the detection should happen in real time, your performance will degrade exponentially. Okay, that is true. If you can ensure that the detection is happening in real time with very good accuracy, that will be the best novelty. Okay. Device diversity, behaviors vary significantly across devices. This we have discussed, depending on how much power do we have in IoT devices. Based on that, they can perform differently. Okay, they can behave differently. If you update the firmware, then also the behavior will change, right? Because of this is the biggest challenge, to create a training data set. Privacy trade-off. So here, if you want to work on federated learning, it is very difficult to get very good accuracy, because now we have a very restricted amount of data on which we want to take some decision, right? So that's the biggest challenge. If you want to maintain privacy, your performance will be compromised a bit. Okay, so you have to find out again the trade-off between these three things. Now, real time, performance, and privacy. Coming to future directions, explainable AI. Then we have basically, you can use this because everything that we talked about is, that is completely black box, right? So it's better if you follow the explainable AI part. Policy driven response, automated mitigation based on AI insights. Predicted learning, this one we have already discussed. Why to use predicted learning? To ensure that the privacy is not compromised. Standardized benchmarks. So this is the problem that we are facing. We don't have proper benchmark because we don't have a good data set for that. So coming to the summary, we have discussed encryption is essential, but a lot of issues also come with that. AI provides solution to that, but the problem is, again, it is not known till now that which one will give better result for us. So it's a hot topic. It's a hot research domain. One of you mentioned Gen AI also. That is good research domain, by the way. A lot of issues will be there, but that is a completely new domain. Okay. How to use Gen AI for encrypted traffic? Practical deployment, integration of tools, models, and domain knowledge. We will see a lot of tools will be there for NDN, a lot of tools for data capturing, a lot of tools. Then again, you need to use a lot of tools for your machine learning deployment also. So all these things create a lot of issues with the practical deployment. So with that, I will stop my presentations, and questions are most welcome. If you have any questions, you can let me know in the chat box. Any questions? Okay. Okay, can't we use already available data from MIT BIH? I'm not sure if basically you have this network traffic data present in MIT BIH. I'm not sure about that. They have normal data set. We do not have network traffic in them. Okay. So if you want to work on network traffic, then you have to download basically a data set where actual network traffic will be there. And by the way, network traffic is in format of PCAP file. Okay. Please remember that. Okay. You need PCAP file if you want to work on this research topic. Okay. So we are basically talking about how ECG devices are communicating with a central database. Okay, we are not talking about individual anomalies in ECG readings. Okay, we are talking about the anomalies in the overall ECG database. Any other questions?
Nikhil sir, no more questions, which was being posted in YouTube. All the questions are already been posted into MS Teams.
Okay, perfect. Okay.
Thank you, Nikhil Tripathi sir. It's my privilege to thank the guest of this session 6 FDP guest. We are truly inspired by the way you connected the theoretical concepts with the real world applications, sir, making this complex subject more approachable and relevant. Your guidance today will undoubtedly strengthen our confidence, the participants' confidence in exploring and integrating all the techniques, whatever you have told, sir. Thank you, sir.
Thank you, Dr. Mani. Thank you for the opportunity. Yeah.